Severino, a la orden ya de empezar, ¿no? ¿Dónde está Severino? Pero guardarlo en sitio. Muy bien, buenas tardes o buenos días. Después de la ordalía de conseguir que haya una foto de familia en la que estén los que tienen que estar, veo con tristeza que mi secretaria me ha puesto el discurso de mañana. Voy a hablar en español. I'm going to talk in Spanish because one of the priorities of the Fundación Ramoneses is to foster the use of Spanish language in science whenever that is possible, assuming, of course, that English is the vehicular. Muchas gracias, hombre. Muchas gracias. Y os aseguro que no es demagogia. Bien, en primer lugar quisiera dar la bienvenida a todos los participantes y agradecerles muy de corazón que llenen hoy esta sala para una causa tan digna y tan noble como la que nos reúne hoy en día. El capítulo de agradecimientos, mis agradecimientos a la Agencia Estatal de Investigación, al Ministerio de Ciencia, Innovación y Universidades, a FECIT, al Ministerio de Transformación Digital. Ya ando con cuidado porque como no sé cómo han cambiado los nombres de los ministerios, no sé si me voy a equivocar, pero bueno, me perdonarán los ministros. Así como a los socios internacionales europeos que han colaborado en este evento. Un agradecimiento muy especial a los representantes de los proyectos QuantERA y Quantum Flagship por el apoyo a esta iniciativa y por presentarnos hoy sus interesantísimas reflexiones. Por supuesto, en last but not least, a las autoridades presentes, a la secretaria de Estado Carmen Artigas, que está llegando, a la secretaria general Raquel Lloti, favorita de esta fundación, a Eloísa del Pino, otra favorita de esta fundación, presidenta de CSIC, a la secretaria general Teresa Riesgo y a Tomás Skordas, que está por ahí, representante de la Comisión Europea, tan sumamente importante en la organización de este evento. Para la Fundación Ramón Areces es una satisfacción y un privilegio organizar y acoger lo que es sin duda la conferencia más importante sobre tecnologías cuánticas en Europa. La Fundación Ramón Areces es desde su origen y su trayectoria hasta la actualidad una fundación de ADN científico cuyos objetivos principales son fomentar la investigación científica y técnica, formar capital humano en las áreas de las ciencias de la vida y la materia, ciencias sociales y humanidades, y sobre todo, presentar a la sociedad española la vanguardia del progreso científico y tecnológico. Y ello lo hacemos también en alianza con los principales centros tecnológicos del mundo, como puedan ser el MIT, Harvard, LSE, Instituto Weizmann, Oxford, etc. La física y las tecnologías cuánticas son temas a los que prestamos especial atención desde la Fundación Ramón Areces. Y quiero entonar aquí un especial agradecimiento al profesor Manuel Aguilar, con quien llevo trabajando en estos temas desde hace más de 20 años y que ha sido un artífice fundamental en el desarrollo de la física en la Fundación. No por nada, en 8 años, el profesor Aguilar nos ha traído más de una veintena de premios Nobel de Física. Y a Juan Ignacio Cirac, que lo asimilo. Juan, bienvenido. Hay un campo más novedoso y con mayor futuro que el de la tecnología cuántica. Pues por eso estamos contentos de acoger este evento hoy aquí. El tema es tanto más atractivo cuanto que los seres humanos no estamos familiarizados con estas escalas espaciales. El cerebro humano no ha sido entrenado para procesar fenómenos a estas escalas. Tampoco lo estamos para escalas espaciales muy grandes o escalas de tiempo infinitesimales. Nos complace también sobremanera colaborar con instituciones públicas y privadas especializadas en estos temas, así como con la Comisión Europea y sus distintas plataformas, que siempre son garantía de profesionalidad y buen hacer. Es también para nosotros importantísimo colaborar con la Administración española, en un año en el que estamos ejerciendo la presidencia del Consejo de la Unión Europea. Nuestra institución está prestando todo el apoyo que puede a algunos de los eventos más destacados, como es esta conferencia y la Conferencia Europea de Diplomacia Científica, que acogeremos también en este auditorio el próximo mes de diciembre. Para nosotros, Europa es un referente fundamental que en este campo concreto de las tecnologías cuánticas está llamado a jugar un papel de primerísima importancia y estamos encantados de colaborar con estas plataformas europeas. Resulta, por último, obligado a constatar la significación de la revolución científica que está ocurriendo en el mundo y que para los que no somos especialistas resulta cada vez más difícil de captar. Ayer, sin ir más lejos, en esta fundación tuvo lugar un interesantísimo seminario sobre los retos de la ciberseguridad y su regulación jurídica. Y constato que cuanto más profundiza uno en estos temas, son más las preguntas y menos las respuestas, por lo menos en lo que a mí concierne. Asimismo, quisiera por último agradecer muy de corazón la presencia del profesor Juan Ignacio Cirac, un vieux habitué de esta fundación, a quien tenemos un enorme afecto, y de los profesores Serge Haroche y Anton Zeilinger, premios Nobel, cuya participación realza de forma sobresaliente el nivel de este encuentro. Un saludo muy especial al profesor Zeilinger, al que creo haber conocido en mi etapa de embajador de España en Austria. Muchas gracias y tiene la palabra, sin más dilate, Dominique Espriu. Muchas gracias.
Good afternoon and welcome to the meeting on quantum technologies in Europe. This meeting is one of the many events organized on occasion of the Spanish Presidency of the European Union during the current semester. This gathering is organized by the QuantERA ERANET and the State Research Agency of Spain, with the collaboration of the Quantum Flagship, the Ministry of Economy and Digital Transition of Spain, and the Spanish Foundation of Science and Technology. My first words are therefore to express my gratitude to the organizations and entities mentioned. Altogether, they will make of this a truly remarkable event. I would particularly like to thank Ambassador Raimundo Pérez Hernández, Director of the Fundación Ramón Areces, for all the generous support they offer. Thank you, Ambassador. Just looking at the audience in this hall, taking note of all the many outstanding scientists and policymakers present here, it's obvious that a lot of interest has been triggered by this event. I am sure that nobody will be disappointed. Quantum technologies are coming to the verge of making profound advances that will leave an imprint in our society. It is now 100 years from the quantum revolution. In 1923, just 1 century ago, in 3 remarkable articles published in the Proceedings of the French Academy, Louis de Broglie proposed the concept of wave-particle duality. That's exactly 100 years ago. However, it seems to many of us that never has been the word quantum heard so often as it is today, in these days. Leaving aside the hype, progress in many realms has brought new manifestations of the quantum phenomena to a point where they might and probably will impact on us in just a very short times. And I conclude, let's move on. This afternoon's session will be divided in 3 parts. A first part consisting of a policy session, followed by 3 keynote presentations by Professors Cirac, Haroche, and Zeilinger, and ending with a panel discussion. But before all this, let me call now Professor Konrad Wacek, the QuantERA Scientific Coordinator, to the floor. Thank you.
Hello, good afternoon. I have a real honor to welcome all of you on behalf of the QuantERA program, which is really delighted to support this very special event and to contribute to its program. I guess many of you know very well the QuantERA program in one way or another, but for those of you who have not heard about it, let me just say that QuantERA groups 40 research funding organizations from over 30 countries, and its main goal to support quantum technology research in Europe. The basic way is to organize on a biennial basis calls for research projects. Those calls were organized in 2017, 2019, 2021, and now we are concluding the 2023 call. And so far, altogether, more than 400 research teams have been supported with QuantERA funding, and the total budget that went for research is approximately 120 million euros. And we very much hope that this biennial tradition will continue in the coming years. QuantERA program formally started in 2016, so we are now in the 7th year of the program, and it received a lot of support from the research community from the very beginning. I do remember email messages exchanged with Professor Anton Zeilinger, with whom we are here. Thank you very much, Anton, for your support from the very beginning. And I believe Professor Arosh was also very helpful in establishing QuantERA as a Europe-wide research funding network. So in some sense, QuantERA can be viewed as a precursor of many other great things that came along, the quantum flagship initiative, of which QuantERA is a proud element, proud member, as well as other infrastructure initiatives that are currently undergoing. So apart from funding research, QuantERA also supports other activities, for example, promoting responsible research and innovation. And one thing I would like to advertise right now, if I could have 30-second commercial break, QuantERA just is very happy to present a report on public policies in Europe, which is just off the press. It is a very good tool to map what is happening in your country compared to other European countries, and you are welcome to pick up your own copy from in front of this auditorium. Thank you very much, and welcome.
Thank you very much. Now I call Professor Dr. Raquel Giotti to come here, to take the floor and address a few words to us.
Embajador, querido Raimundo, profesor Espriu, director general de la Agencia Estatal de Investigación, profesor Van Aztesk, coordinador científico de QuantERA, Mr. Skorder, Deputy DG of DG Connect, Professor Chirac, Professor Aroch, Professor Zeilinger, and embajador de Austria, querido Eno. Tengo que disculparme, en primer lugar, porque yo tengo mi discurso en inglés y espero que el director general de la Fundación Ramón Areces me lo perdone por no ir cambiando sobre la marcha. And I want to start welcome all of you to this very important conference organized by our State Research Agency and the Spanish Ministry of Science and Innovation with QuantERA and in collaboration with the Ministry of Economy in Spain, in the framework of the Spanish Presidency of the Council of the European Union, as already mentioned by the director of the Spanish Research Agency. And I think that this is a very good opportunity to very briefly outline the 4 priorities of our presidency during this semester. The first one is the reindustrialization of the EU and guaranteeing its open strategic autonomy. Second, advancing in green transition, looking for sustainable practices and environmental responsibility. Third, promoting greater social and economic justice, striving for fairness and inclusivity. And fourth, strengthening European unity, fostering a more integrated and robust union. And aligning with these priorities in the realm of science and innovation, we have designed a tailored approach for our scientific policies, primarily focused on the Council conclusions that we expect to be approved on December. We have three key priorities. The first one is the use of science for the public policy process, enhancing knowledge to improve citizens' lives and strengthen democracy, improving cooperation and territorial cohesion through R&I, focusing on the role of the regional and local innovation ecosystems. And the third one is analyzing the policy impact of the Recovery and Resilient Funds on the European research area as a qualitative leap in European R&I policies to improve competitiveness and welfare. And in addition, we also expect that under our presidency, it is adopted the EC recommendation. One of the great challenges that we are facing, such is the need to attract and retain our scientific innovation and entrepreneurial talent in Europe. And as you can see, all these priorities are not thematic-oriented, but I think that they look very pertinent and related to the topics discussed in these days, as are the quantum technologies and how they can contribute to face global challenges. On one hand, we acknowledge the pivotal role of science and innovation in supporting policymakers and emphasize the necessity of establishing effective interfaces between the two. On the other hand, we recognize the transformative potential of research and innovation investments in various sectors related to quantum technologies. And furthermore, we delve deeper into how R&I investments in these technologies can foster cohesion in both regional and national territories. Last, but certainly not least, we underscore the imperative of revising the framework for human capital in quantum technologies as a crucial step in maintaining competitiveness and in the coming decades. In the past decade, the rapid advancement of quantum technologies has transformed the scientific and technological landscape globally, and Europe has emerged as a key player in this exciting journey, propelling research and development projects through strategic initiatives, notably, of course, the ERANET, QuantERA, and also the Quantum Flagship, and also the UPC, among others, and that has been supported by the European Commission. Europe has concentrated very important, significant efforts on developing quantum computing, quantum communication, and quantum sensors. And countries such as Germany, the Netherlands, France, and Spain have led ambitious projects, some of them backed by the European Union, with the aim of harnessing the revolutionary potential of quantum technologies. The Spanish Ministry of Science, Innovation, and now Higher Education, universities, is very aware of the disruptive nature of quantum technologies and the direct effects that it will have in the industry and society in our country. To face the opportunity to respond to the challenge of being among leaders in this area of knowledge, our ministry is committed to firmly supporting the Spanish scientific community that works in the four major areas of quantum technologies, such as quantum computing, communication, simulation, sensors, and metrology. The Spanish Ministry of Science, Innovation and Universities, as an integral part of these joint European efforts, has made significant contributions, mostly through our state research agency, the AEI. The AEI finances experimental and theoretical groups related to quantum technologies, both in the European and national framework. Within the European initiatives to stand out QuantERA, where the AEI with the Science and Technology Foundation FECIT participates as a partner and funding agency. And between 2017 and 2021, in the three previous QuantERA calls, the AEI has funded 27 Spanish participants with 3.7 million euros. In the current QuantERA call, the AEI will finance Spanish groups with more than 1 million euro. And between 2023 and 2025, now looking to the future, the AEI plans to dedicate 45 million euros to its calls for human resources and projects to finance actions related to quantum technologies. It has to be also referred as a new tool that we have launched in 2021, taking profit of the Recovery and Resilience Facility, as it is the case of the program called Planes Complementarios, complementary plans, as a co-funding and co-programming exercise done by the state with the regions in 8 thematic areas. And one of these thematic areas is precisely quantum communications with an amount of 73 million euros of investments. As I pointed out previously, all these efforts will not work if we are not able to attract and retain talent, the talent that we need in Europe. Postdoctoral fellowships and researchers' consolidation initiatives have been pivotal components of the AEI efforts aiming to strengthen the research landscape in Spain. And the recent trends in the number of researchers and positions covered through the AEI programs revealed an exponential increase. Over the past 3 years, there has been a notable and unprecedented doubling in both the quantity of researchers benefiting from these programs and the number of permanent positions filled within the Spanish National Research and Innovation System. As of now, the investment in grants for the postdoctoral phase of contracts that we call the Programa Juan de la Cierva y el Programa Ramón y Cajal stands in quantum tech more than 10 million per year. And these figures underscore what is most important, that is the commitment towards supporting and fostering research talent through these prestigious programs. As a partner of QuantERA, our ministry, through the AEI and FECIT, led the preparation and report distributed at the Quantum Technology Public Policy Report that has been already mentioned. And this report underscores Spain's active commitment in the quantum domain. Moreover, through the AEI's international collaboration project calls, with our ministry will finance the participation of research groups from universities and non-profit research organizations in projects from competitive calls in which Spain participates, such as the Euro HPC, GU, or the new CHIPS Act, CHIPS GU. In summary, and to conclude, the rise of quantum technologies in Europe, supported by initiatives like the ERANET QuantERA and the Quantum Flagship, is complemented by the Spanish investment. This collaboration not only propels research and development, but also strengthens international cooperation, positioning Europe and Spain specifically at the forefront of the quantum revolution and promoting the practical application of these technologies. The AEI, with its strategic focus and funding instruments, plays a pivotal role in this exciting journey towards a quantum future. And I would like to conclude again, wishing you all a very successful conference. Thank you very much.
No? So let's go to the... Oh, okay, good, thank you. So now we finish this introductory part, and now we move to the policy session. So one of the 3 main parts in this afternoon program. So the first speaker will be Dr. Thomas Escordas, Deputy Director General for Communications, Networks, Content and Technology of the European Commission, who will talk on the strategy of Europe in quantum technologies.
Dear State Secretary Carmen Artigas, dear Secretary General Rachel Yotti, dear Ambassador of the Foundation Ramona Reches, dear Professors Serge Roche and Anton Zeiliger, dear distinguished guests, I'm super, super pleased to be here together today with you to this important event on quantum. Let me express, first of all, my thanks to the Spanish State Research Agency, to QuantERA, but also to the Foundation Ramon Areces that is hosting us here and who have also organized all these events. As you know, since the 90s, actually, quantum is a strategic emerging technology, a strategic emerging area for Europe. And since the 90s, Europe has financed already several hundreds of projects for an investment of which is more than €500 million so far. So I think this event here gives us an excellent opportunity somehow to reflect on the importance of the EU leadership in quantum technologies. So I would like, therefore, very quickly to go through and assess what are, in our view from the Commission, the strengths that we have here in Europe, what are our main achievements so far, which areas can we still improve, and maybe what would be some reflections on what would be the best way forward. First, let me start with our strengths. So the first and most important, we have talent and we have people, in the sense that we have the highest concentration of quantum talent in the world, with 230-something scientists and experts per million of inhabitants. And to be able to compare it, the equivalent figure in the States is only 120 and 170 in the UK. So I think also that we can be proud of the fact that we have the highest number of master's degrees in quantum. We have world leadership in quantum scientific publications. We have certainly also a very growing number of portfolio of patents. And last but not least, very, very important, Europe is one of the pioneering regions of the world, not only in quantum, but also in science quantum, since we have many Nobel laureates, and we are really pleased to have today Professor Auroch and Professor Zeilinger, who are honoring us today with their presence here. Now, with quantum being recognized, the strategic asset for Europe, since 2018, we decided to launch the quantum flagship, and I'm pretty sure that many of you are already participating. So 1 billion euros, 10 years duration. I think these are the kind of things that you do not find easily in our program in the European Union and in the European Commission. Most of the projects that we have are 2-3 years, 4 years maximum, so defining something that goes for 10 years is already a huge exploit, I would say, thanks to you, by the way. And ever since, because of the flagship, we have now many member states, I think Ms. Yotti has already highlighted some of those, that are investing heavily in quantum. And ever since, actually, we, the amounts that have been announced in the from public investments in quantum are close to 8 billion, actually even more than 8 billion euros. Now, of course, in addition, we have QuantERA, and I think this is also one of the ways where the scientific community is really excelling in science, since QuantERA, since 2013, if I'm not wrong, is bringing together 39 agencies from 31 countries to coordinate really world-class and cross-border quantum research. But that's not all. I think also that our industry is also lining up. And Europe is now the home of almost 25% of the world's SMEs in quantum. And we have become actually a world-leading startup scene, which is, we have more than 25 startups today, and which is quite similar to what the US is having. And actually, with all these actions and all these approaches, our quantum ecosystem is really growing, and is growing fast. So I think these favorable conditions have given rise now to a strong track of record of scientific and technology achievements, and these are further supported by a number of ambitious R&D projects that are financed through the quantum flagship, but also through the national initiatives, and that are helping Europe bring really at the forefront, bringing Europe at the forefront of our science and technology achievements and world-class successes. Let me give you some examples. I will start with quantum computing, maybe the most, I would say, challenging, but also the most expected area and most interesting area from the point of view of having highest impact of what will happen out there when we will have a universal quantum computer. In quantum computing and quantum simulation, actually, the European Union covers all possible areas and platforms of quantum computing and quantum simulation. The reason is simple, is that we don't know yet who will be the winner, if there will be one single winner. So it's better that we bet on several possible platforms and let 1,000 flowers bloom, as we say. So, and from there, having the one that will be emerging or several ones that will be emerging, and actually we find it's very, very good to have also a good competition about who will be the winning one. And here we have nothing really I would say, to envy from the Americans, apart from the fact that quantum computing in the States is really a matter for big companies, which is another story. I'll come back to that in a moment. Now, in Europe, we can be proud, for example, that we have already quantum platforms, like, for example, the one that is based on trapped ions, but it's not the only one where we have already reached 30 qubits, and we are now in other platforms also advancing quite quickly to reach the 100 qubits and possibly much more in the years to come. We are leading also in cold atoms. We are also leading in diamond nitrogen vacancy center platforms. And as I said, we are competing on par in all the other computing platforms. So we are, I think, among the world leaders, not in all technologies, but certainly in some of the important technologies that are related to quantum computing. Let me move to quantum communications very, very quickly. So here, I think we are having world-class research again, and I would actually say we are world leaders. And we have here the first 3-node quantum network that has been implemented alongside the world record quantum memory. And together with the first prototype of quantum repeaters, we start having a little bit the first instances of what could be the quantum web or the quantum internet of the future. Now, in sensing also, it's not bad at all. And our researchers have already built an integrated optical atomic clock, which is outperforming standard microwave clocks. At the same time, we have many advances in many of these sensing capacities. For example, we have now improved sensors that are based on diamond NV centers that I mentioned before, which both go for much better medical imaging, offering, for example, 40 times faster diagnosis of cardiovascular or kidney problems, but also offering 1,000-fold better resolution of magnetic and electric fields, making it possible to monitor chemical structures at a single molecular level. But it's not only about funding promising research, and in particular longer-term research, which absolutely is needed. At the same time, even if we know that quantum is still an emerging technology, that it may take several years before we reach really commercialization or industrialization and commercialization, we need somehow to create more spin in Europe from the point of view of our startups and SMEs to be able, for example, to create the first quantum leading infrastructures deployed all over Europe. This is the way that we think we can create lead markets for our industry, for our companies, for our startups, but at the same time, these infrastructures are really a kind of appealing element for many of our scientists, for many of our users to get used to quantum technologies. Let me give you 2-3 examples. In the Euro-HPC joint undertaking that was mentioned also by Ms. Yotti before. Here, we're not only acquiring supercomputers, high-performance computers, and I know that many of you are working in this field, and we are really proud about the achievements we had the last few years. Here, we're also acquiring quantum computers. We are taking the risk of acquiring quantum computers even with a small number of qubits, for the sake also of starting, integrating them together with our supercomputers and creating the first federated network of supercomputers and quantum computers, with quantum computers eventually acting as accelerators of the standard supercomputers. Why we do that? We know that these are noisy machines. We know also that it will take several years before we have a quantum computer which could become something much better than what we have today. But that's this, we are certain, however, that quantum computers will not replace supercomputers, and that the future may be also in this hybridization that I mentioned before. And I think this is certainly one of the ways to go. So our ambition is to create these hybrid structures in the 2-3 years from now, and make them widely available through the cloud, if it is possible, to our scientists, to our users from industry, and create a number of applications we need for them to start working and to start experimenting with these facilities. So that's the ambition, and I can tell you the other ambition, and hopefully the Council and the Parliament has also supported it, was not to buy American, but to buy European. So we buy machines. These first 6 quantum computers and quantum simulators we buy, they come from startups. So, and the second generation of those will be the same, that probably we'll buy in a few years from now. And the same for the third generation. This is the way we can make these lead markets I mentioned before, but we can also push our SMEs, to industrialize as much as they can with the help of our scientists, with the help also of our large industry, if this is possible. EuroQCI, communication infrastructures. That's another big infrastructure that we are building right now in Europe. I hear the Americans saying to us, are you sure that you want in the area of quantum key distribution? Professor Zeilinger, does it say something to you? So the Chinese, we know they've already built a network of those several years ago. I hear our scientists sometimes saying that we're a long way to go before we have a QKD infrastructure in Europe, which is certainly true, but you have to start from something. So we start with quantum random generators, single photons, whatever you have there, and the first QKD machines that some startups are producing, and we start deploying the first QKD networks in Europe. All member states except one, 26 member states, are now deploying these infrastructures. So our ambition is what? Is we deploy the first generation of technology. The same happens also in the space. So we are working with the European Space Agency to have first satellites that would provide quantum keys all over Europe, and not only, by the way. So we will create an integrated network, the first probably integrated network for Europe and probably also for the world. And we will start using that, knowing that in parallel, we have to continue our efforts to create the quantum communication infrastructure of the future. I mentioned the quantum internet before, and that's the way forward. So, and as new protocols, as new quantum repeaters, etc., would come at the forefront, our ambition is, of course, every time to create a new generation of those testbeds out there and create the possibility for a large number of use cases. I mentioned also its lead markets for our industry and for our SMEs, and that's the way also we need to position ourselves to look into the future. So that's our ambition, and that's what we are doing right now. Of course, you will say all these are great developments, and we are happy about that, or we can be happy about that, but at the same time, we have quite a number of weaknesses that we would need to address. These mainly concern the level of private investments we have in Europe, the access to financing, the access to talent, and then a little bit also some more coordination between the member states. Let me start with the engagement of our large industry. I think here we have a real problem for the time being. Our large industry is watching us, but is not putting their money in the pocket. So there is something there. So why is this happening? Frankly, they believe that quantum is going to be a technology for the next 15 years. So they believe that they should not take the risk right now, but when it will happen, as it happens with generative AI, it will be too late. We will miss the train. So that's why I mentioned before, we're investing and looking at this from a different perspective. Now, if you want to compare where we are with Americans, where I mentioned quantum computing is typically an American story of large companies, I will not cite them, you know them. Annually they invest 5 billion euros on those, and in Europe, our large industry is investing 3 to 4 times less. That's the situation today. I'll come back eventually how we can address that situation. Access to financing. I mentioned to you we have 25% of the quantum tech SMEs globally, but at the same time, they are only raising 5% of the global financing. So that's the situation we're facing today. And then access to talent. Yes, I know we're very happy that we have a lot of students, but at the same time, we are here now many SMEs, many startups, and some of the large companies that take the risk to go one step further, telling us we are lacking talent. We are lacking the possibility to get more people in quantum, and we need to do something. So they're struggling, in fact, to find the good people and to find the good engineers that we need to make one step further. And finally, let me say a few words about member states, about our member states, and about the Union. So it's good that we are launching more and more national programs. Definitely, this is the way to go. But maybe we still need to be a little bit more among ourselves, that is, coordinate a little bit further our different activities and move ahead in a kind of more coherent way. I'll come back to that in a moment. So, okay, you can say, well, maybe the Commission is right in having detected these weaknesses, and maybe these are things that we need to improve in the future, but how? Let me give you some examples. Certainly concerning large industry, I think we should all take the kind of mandate to go and approach them and explain to them that quantum is not in 15 years from now. There are low-hanging fruits out there, and we can already start investing in a number of areas, starting from quantum sensing and continuing with some other components and devices. And therefore, I think this kind of campaign, we need to have it relatively quickly. And then the second one is through a number of activities, we need to more integrate large industry with startups and SMEs in common projects. We started doing that, but I think we need to do even more. And the third one, it would be good somehow to see how we can make sure that our industry is providing some financing also for our startups. They have separate funds, and sometimes these funds go to other companies for whatever reason is their choice. But I think we have to convince them that there is also scope to provide some of these funds for our startups. Since I'm talking about companies, the big challenge for us is it's good to have startups, and at the same time, they need to scale up. So what do? This access to finance that I mentioned before. So look, we started putting in the European Innovation Council now a dedicated fund for startups, for all these emerging technologies. And I must confess that out of the 25 companies, SMEs that we have right now, startups, 19 are already financed by the European Innovation Council. Is it enough? Certainly not. It's a first step. But the big challenge is not to get, the first funds. The big challenge is the scale up. And there, we need to do something different, which is something we have never done in the past, is to make a continuum between, the first steps and then the real scale up by providing access to any kind of financing, equity or whatever this is, loans or whatever this is, for the longer term. That's the only way for our startups to develop further and become the big companies of the future. By the way, the European Investment Bank, in cooperation with us and many of the member states, I must also admit, has now set up a big fund, more than 8 billion euros, if I'm not wrong, saying that this is the fund for emerging technologies, actually most of them being digital, and quantum is a particularly, I would say, popular area for being financed, and this is what's happening out there. Now, the other big thing is how do we promote industrialization? I talked to you about lead markets. I said to you a little bit about the infrastructures, but is this enough? Certainly not. That's one of the reasons why we have introduced, I think, again, Ms. Yotti mentioned it before, we need to make sure that we don't stop at basic research, and we push also, as much as we can, the limits for accelerating, eventually, the industrialization of quantum processors, quantum components, etc. That's the reason why we have introduced in the CHIPS Act 400 million euros to be able now to invest into the kind of industrialization of standard quantum processors and components, and convince industry that there is time now to develop a roadmap, and they are right now doing that could serve us to make the first calls in this area. And then we have quantum sensing, where things are maturing. So we took the bet to put in the next 2-3 years, 2 major initiatives. One, to create a large pilot network of quantum gravimeters all over Europe that will be composed of both terrestrial gravimeters, but also airborne, and later on also space gravimeters, with the objective, to use those to be in a position to detect these changes in the gravity, of the Earth, which would allow us then to detect what's going on beneath, several actually kilometers beneath. So you can imagine that with drought coming, it's important to be able to detect the water basins. It's important also to be able to detect and monitor what will be happening with CO2 sequestration. It will be important, for example, in Iceland to monitor the volcanic activity and the way magma is coming up, up to the surface. So they were the first, by the way, to say we need this kind of network. Can Iceland be part of this? As soon as this is developed, and this is under discussion right now for having the finances to make it happen, as I said, in the next 2 to 3 years. And in sensing, we took another bet, which is to make sure that some of the first magnetic resonance imaging facilities go to hospitals. So quantum-based, because as I said to you before, the quantum is bringing the kind of resolution and the kind of accuracy we don't have. But so especially when you detect cancer elements. And this is the other big bet, so that we will promote 1 or 2 of these devices and install them in a pilot mode in a few hospitals, and we'll see what will happen, so to create a first lead market also there. Big talent, big question. So yes, we have an excellent track record in talent, as I mentioned before, and certainly the investments we do in basic research, long-term research, in infrastructures is a kind of motivation for our people to stay in Europe and to work in Europe. But certainly this is not enough. So we need really innovative initiatives, and I challenge you to come and see us and tell us what we can do all together to make things happen, to attract the young people beyond the masters, to make sure that we have all the necessary skilled workforce, but also to attract, I would say, talent from outside Europe. I know it's a delicate question, now that immigration is one of the central points, again, to several of our governments, but I think there's no other way that we can also address some of those issues than being able to attract the best Indians, the best Brazilians, and maybe other parts of the world to make sure that these work with us and actually stay in Europe also. Don't misunderstand me. I'm not saying this is the priority. The priority is to make sure also that our students understand what is quantum, and we attract them in quantum. Now, the big thing is AI, so everybody goes to AI. I would like also to combine AI and quantum, and this is possible, believe me. Because, for example, part of the training that we have for big AI models could be based on quantum computing, just to give you one example, but there are others. So I think this is a little bit the way we're thinking in the Union, the way we're thinking in the Commission, through the big lead of Commissioner Breton, who is probably, a big fan in quantum. And therefore, through his motivation and through his commitment, we are where we are today, but definitely we want to be much, much, more ambitious than what we have done so far. I'm coming therefore to a little bit to what we can do together with the member states now. And I would say, good to have all these 8 billion, but we need to better coordinate our efforts. And to better coordinate our efforts means that we need to work a little bit better together and maybe fix some common targets for the years to come. And then maybe making sure that our teams, which work in different areas, work for these common targets, and that we achieve the way forward. Actually, that's the only way that we can also compete with the big American companies. Europe has to stay at the forefront of innovation, and the only way to do that, since we don't have large companies doing similar things, is to innovate all together, to bring our efforts together, bring our skills and our knowledge together, and make it happen for the future. Now, certainly with all this, you may understand that we took a number of decisive steps also to make sure that we develop further, as I said before, the quantum ecosystem, but at the same time, our capacity to develop our economic security and also our strategic autonomy. So actually, we are in the process of making a large study with all the member states on what are the risky quantum technologies, risky from the point of view of a risk assessment, identify these risks in the quantum ecosystem in terms of also sensitive technologies, and then, based on these results, take the necessary actions. This doesn't mean, and don't misunderstand me, that we're only introvert and inside looking. Quantum is an area where we have to work much more than what we do actually with our strategic partners internationally, especially the like-minded countries that are sharing the same values as us. You know much better than I that the challenges that we are facing in terms of S&T are much bigger than what we can do alone in Europe, and therefore we need to have a way to work with them on these common challenges. We need to have a way of putting money together with some other regions of the world, with the US, with Canada. Already we did it, but we need to do much more. With Japan, there is now digital partnerships that we have signed, and even with South Korea and India. So these are the first target areas, and you will see calls coming on those very, very soon. So, in conclusion, and I think I was a little bit longer than I should have done it. I mean, anyway, in conclusion, I think that my main message today is that even if quantum is, for some of you and for some of us, and certainly several years before it can really mature, we need to continue actively supporting research and technology developments, including basic research, by the way, while at the same time already looking at opportunities to be able to exploit first emerging market opportunities in the quantum field. That's the way we can only go ahead, and I can assure you that the Commission's high-level ambition and its eagerness, there is eagerness to work all together to make it happen. We want Europe to be at the forefront of research and deployment and to be the best place to do quantum globally. Therefore, somehow we want Europe to become the quantum valley of the world. It is my last message, maybe. It is, we should not forget also that when we are in this kind of gatherings, we know the importance of quantum, but it's not necessarily the case of the people out there. So if they see all these billions being invested in these technologies, they will start wondering. And when you start saying, I'm working in quantum, they look at you like you are an extraterrestrial. I mean, so nobody knows what is quantum, basically. So we need really to, you as scientists, and I think all of us as policymakers and from the public domain, and also our industry players, you know, we have, I think, a moral obligation to be able to go out there, disseminate what quantum is about, explain, and take the time really to engage our people and make them commit to our causes. That's the only way we can succeed it, and it's not an excuse by saying, they don't understand anything. On the contrary, the more they understand, and the more even sometimes they share some of the moral risks and ethical risks we may have also in quantum in the future, I think you understand what I'm trying to say, then the better it's going to be because we'll have the public supporting the way forward. So that is for today my main messages. Thank you very much. I wish all of us a very, very successful conference.
Thank you, Dr. Escordas. Now I call Mrs. Carmen Artigas, Secretary of Estado, State Secretary for Digitalization and Artificial Intelligence.
Good afternoon, Deputy Director General, Secretary General, General Directors, authorities, distinguished guests, ladies and gentlemen. It is a pleasure for me to participate in this presidency event that we co-organize with the Ministry of Science. I am humbled to be surrounded by no less than 3 Nobel Prizes and all the quantum ecosystem in the EU and in Spain. Just as technological waves pass by, during the Spanish presidency, we have talked about AI, data, federated cloud, neurotechnologies, but it was time that we also talked about the potential of quantum technologies for the competitiveness of the European Union. Forecasts from some studies estimate that the size of the quantum technologies market will exceed 100 billion euros in the next 15 years. And we need to be ready to tap on this potential, not only from the scientific development side, but also for our industry. As we venture into this uncharted territory of quantum technologies, we find ourselves on the verge of a revolution that holds the promise to reshape our world in ways previously unimaginable. Quantum technologies harness the peculiar behavior of particles at the subatomic level, introducing complexities that demand unprecedented levels of precision and control. Quantum computers, for instance, have the potential to solve complex problems at speeds that surpass the capabilities of classical computers. While this opens new frontiers in areas like cryptography and optimization, it also raises concerns about the security of existing encryption methods, as quantum computers could break them at ease. Quantum-resistant cryptographic algorithms must be developed and implemented to secure sensitive information in a post-quantum era. Nations can adapt and fortify the digital infrastructures against quantum threats and will be better positioned to protect their interests in an increasingly interconnected world. For this, we need to ensure there are enough investment available and made in these technologies so that this helps to reinforce the value chain for the production and development of quantum technologies in Europe. These investments should also help find concrete use cases of quantum technologies in the market. This is why, in Spain, we launched the Next Tech Fund, a fund of funds with 8 billion euros available to support deep tech and scale-ups in our country. In Spain, we are determined to lead this revolution and make the most of the opportunities it offers with our national strategy on quantum technologies. Today, I will share with you 5 fundamental pillars of action that will guide our path to the quantum future and be positioned in the leading seat of this technology globally. First, Quantum Spain, the embryo of our revolution. We have already taken the first step with Quantum Spain, the pioneering project that lays the foundation for the construction of the 2 first quantum computers in Southern Europe. And I say 2 because we have the quantum computer based on semiconductors and also the quantum computer based on annealing, together with 2 emulators. This together with a high-performance ecosystem led by Mare Nostrum 5, putting our country in a very unique ecosystem of HPC and quantum computing together. This project is the crown jewel. We are building it with 100% components and European companies. So this is really the embryo of our foray into quantum technologies, and we are committing our success and will continue to support it with significant resources and efforts. 2, research and infrastructure, driving knowledge and production. We cannot move forward without solid research in the right infrastructure. We aim to launch the specific calls for quantum technology research projects and strengthen the necessary infrastructure for the production of quantum chips. We are committed to excellence and innovation in every step we take. 3, talent, generation, attraction, retention. The Deputy General has already mentioned that. The real engine of our quantum revolution will be human talent. We will invest in generating new talent, attracting the brightest minds, and creating an environment that retains top quantum experts. Education and training will be our tools to build a highly skilled workforce ready to lead the quantum revolution. Therefore, we're going to launch the program named Q-Talent. 4th, Spanish quantum business ecosystems. Innovation comes not only from large research institutions, but also from entrepreneurial minds leading startups and scale-ups. Through the Next Tech Fund and other initiatives, we will financially support companies at the forefront of the quantum revolution. We want to create a vibrant and sustainable business ecosystem that drives growth and competitiveness. And last but not least, governance, ensuring responsible development. Governance is essential for the equitable and sustainable development of quantum technologies. We will establish a robust governance framework that addresses key aspects such as standardization, industrial property, and disclosure of actions and knowledge. We are committed to being transparent in every step we take and ensuring that the quantum revolution benefits everyone. And all this following Spain's vision of human-centric and rights-oriented digital transformation that we already share in our Charter of Digital Rights. But the important message is that no one can do it alone. Not a single company, not a single country can do this alone. So I would like to emphasize the need for collaboration at European Union level in the field of quantum technologies. We need to look for collaboration in 4 areas. First, it is important to recognize quantum technologies as pivotal for EU scientific and industrial competitiveness. Second, we must envision and foster a comprehensive quantum ecosystem transcending vertical boundaries and finding the use cases across industries. And let me say that it is critical to ensure our open strategic autonomy and to assert our independence in the face of global technological shifts. Third, we need to harmonize EU's approach to quantum technologies, as in this realm, unity is a strength. We need to be able to pool resources from one another, avoid duplication and efforts, and share knowledge. And fourth, we need to make sure these technologies evolve from research to real-world applications. I have no doubt this evolution will ensure that Europe not only pioneers quantum capabilities, but also reaps the practical benefits of quantum technologies in fields such as communications, computations, and sensing. As we stand on the verge of the quantum age, let us not merely witness the future, but actively participate in its design. Let our endeavors be guided by the principles of ethical stewardship, responsible governance, and a shared vision for a world enhanced by the limitless possibilities that quantum technologies offer. In closing, I extend my gratitude to each and every one of you, the architects, the builders, the doers of this quantum future. Together, let's write the narrative of progress where the chapters unfold, not just in laboratories and boardrooms, but in the everyday lives of people, transforming challenges into opportunities and dreams into reality. Thank you very much, and may our quantum journey be one of inspiration, discovery, and unparalleled achievement. Thank you very much.
Okay, so now we'll proceed to the second part. So I now call Professor Philippe Grangier, who will chair this part of this afternoon session.
Hello, everybody. So welcome to this keynote session. So we will have 3 outstanding speakers who will give talks, half an hour each, and then there will be some space for questions and also for space for questions after the talk. So if you have questions, keep them in mind. You may have a second chance to ask them. So my name is Philippe Grangier. I'm working in Institut d'Optique in Palaiseau in quantum optics and quantum information, and I'm also the coordinator of the QCAT, of the Coordination and Support Action QCATs, which helps the European Commission to manage the quantum flagship. So I will introduce the speakers and chair the session. So the first speaker is Juan Ignacio Cirac. So he's a Spanish physicist, director at the Max Planck Institute of Quantum Optics in Germany. And he's a board member of Telefónica, the telecom company in Spain. He obtained his PhD in theoretical physics at the University Complutense here in Madrid. Then he held position in the USA, in Spain, in Austria, and since 2001, he is director of the theory division at the MPQ, Max Planck for Quantum Physics in Garching in Germany. And he is also honorary professor at the Technical University of Munich. He is leading several activities related to the Max Planck Society and to the Munich Quantum Valley. So Ignacio Cirac is an expert in quantum computing and quantum communication. With his collaborators, he introduced the first theoretical proposal for quantum computing, in particular the very famous Cirac-Zoller gate in 1995. He also worked on quantum simulation and quantum repeaters. He developed a theory of quantum networks, of tensor networks, to solve problems in quantum many-body physics. So for his work, he has been awarded many prizes, among them the Prince of Asturias, the Benjamin Franklin Medal, the Wolf Prize, and the Max Planck Medal. He's a member of the Spanish, Bavarian, and German Academies of Science, and he holds 8 honorary doctor degrees. So, Ignacio, the floor is yours.
Okay, so good afternoon, and thank you very much, Philippe, for this kind introduction. And so let me start just by thanking our host, so the Fundación Ramón Areces, for hosting this event. I mean, I have very good connections and relations to the foundation, and it's always a pleasure to be here because of their hospitality as well as the role that they play in bringing science to society. I would like also to thank QuantERA, the quantum flagship, and the EU for the continued support for quantum technologies during the last 30 years. So it has been mentioned previously that it has been very important for the development of the science of quantum physics in Europe. And finally, also, my greatest thanks to the Secretary of States that are present here for the support that Spain is giving to quantum technologies as well. So I have been living in Germany for many years, but I'm very much connected to the Spanish environment, scientific environment, and I think that I've never seen such a support like the one that we have now. So I'm going to talk about quantum simulation. That's one of the columns that we have in quantum technologies. And let me start, yes, with this picture that surprised a little bit the world in 2019. It was a week after I gave a talk here, in fact. And that was a cover page in many newspapers, and it announced that Google had achieved what is so-called a quantum advantage, a quantum supremacy. So for the first time, they had solved a problem with a prototype of a quantum computer in a time that was much shorter than with supercomputers. Of course, this was a problem that was tailored for the system that they had. They didn't have a quantum computer. They had a prototype, was small, had errors, but still, they really proved at that time that with quantum computers, at least with the prototype that they had, there were some particular problems that they could solve faster than any other existing computer in the world. At around that time, there were already many newspapers and media just telling us all the applications that we could have in quantum computation. And in fact, this raised a very big hype. And indeed, I mean, some of the applications that are mentioned here in some other media, then we don't know if they are really like that and if we will ever reach them. We know that with present quantum computers, that like the one that Google was building or the ones that we are building in Europe, this would be very difficult. But nevertheless, I mean, we know that quantum computers really have some promises, and in particular, in few areas. So first of all, we know that if we had a quantum computer, a full-fledged quantum computer, then this would allow to decrypt messages and all our communication systems were on stake. We also know that problems as they appear in science, in physics, in chemistry, but also in the pharmaceutical industry would benefit very much from quantum computers because the computations that they have to do in order to predict the properties of materials at low temperatures or some chemical reactions require such a power that cannot be achieved with supercomputers. We also know that in some problems related to optimization that are of interest of the industry, quantum computers could help. And this is one example, the travel salesman problem, in which you have to go to several cities in Europe. You know the distance between the cities, and you have to find the shortest path that goes through the cities. That's a combinatorial problem that is very difficult to solve for classical and quantum computers, but still with quantum computers you can accelerate a little bit the process. And also, since the results of Google were basically just processing data in a different way, so creating samples in a very special way, then it's a good evidence that quantum computers could also help in data science, and in particular in machine learning. Still, I have two comments here. So first of all is that there are very big difference between the first column and the second column of applications. So the first column of applications, the ones that we know that there is an exponential speed up. So this means that the computational time that it requires to solve this problem in a classical computer grows only linearly with the number of constituents that you have. Whereas the second one, whereas in classical computers, this grows exponentially. And so this means that there are many problems that we would never be able to solve in these particular applications if we don't have quantum computers. On the second hand, the other problem is they have a polynomial speed up. It means that they may accelerate the solution of these problems. However, I mean, it's not clear at which level this will happen. It will happen with prototypes, with the scalable quantum computers. Maybe we need even more powerful quantum computers for that. And the other comment is that probably the most important applications of quantum computer are not here because they still have to be developed. So there is a lot of research behind that has to be carried out, and I will talk about that later on. So regarding devices, we are building devices with different platforms. So, but the situation is a little bit similar to the ones that we had when the first classical computers were built in the 40s. So the quantum computer, you have a picture of the interior of a quantum computer, looks very, very complex. And also the situation is similar because you know that when the classical computers were developed in the 40s, in the last century, the main applications that they had was first for cryptography, so to decrypt messages in the Second World War, and the second one was scientific applications. That was all. So it's the situation that I showed you before. We know that quantum computers are very useful for decrypting messages. We know that they're useful for science applications, and so the situation is very similar. But as you see, classical computers now in the last 80 years, they have many, many applications that at that time nobody could imagine. And in the same way, we believe that by crossing the frontier and having now access to quantum computers, then many other applications will show up, as I mentioned before, in the transparencies that I say that most of the most important applications are still missing. In fact, I mean, there's a very famous statement by IBM directors at that time that were thinking that computers were not really useful, would not be useful. Now, since I'm the first talk here about science, I wanted to give you a couple of hints about quantum computation, and this will be very basic for most of you who are experts on that. But anyway, so let me tell you that quantum physics has a particular aspect that is very different from the physics that we are used to live in our everyday life, and is the existence of superpositions. So we go to the microscopic world, then there are objects that behave in a very special way. So for example, we can have an atom, and an atom you can think of a very little magnet. And this little magnet could have the north pole pointing up, that's what we call spin up, or it can have the north pole pointing down, that's what we call spin down. And according to quantum physics, if these two situations are possible, then we can also have what we call superpositions. And that's a situation where we have at the same time spin up and spin down, north pole pointing up and pointing down, as long as this atom is not disturbed. So if I isolate, we don't look at it, and it will have, it's like living in two different worlds at the same time. The same thing can happen with superconductors. So you can have a small conductor in which the current goes clockwise, or it goes counterclockwise. So we can assign 0 to clockwise, a 1 to counterclockwise. And according to quantum physics, as long as we have this object very well isolated in some special conditions, it can be in the superposition, meaning it has not decided in which one it is. And only when we observe, we will define what is the property of the direction of the current. Now, for quantum computation, it's important that this superposition can be extended when we have many objects. So if we have now many atoms or many superconducting circuits, then you can have many, many combinations of all the possible situations in which these atoms can be, all these spins can be. So for example, you can have all spins down and one spin up, or one spin up, the others down. And then there's an exponential number of configurations, actually 2 to the power n, where n is the number of these bits, quantum bits that you have. And according to quantum physics, you can have a superposition of all of them. So you have like not only just one configuration of the bits, but you have all the superpositions, all the configurations like living at the same time. And of course, it's very special. There is no classical analogy of that, and that's something that is exploited with quantum computers. So sometimes, I mean, this is termed as quantum parallelism, in the sense that you can imagine that a quantum computer is doing many computations at the same time. However, this is not true, and this is not where the power of quantum computation comes. And the reason is because at the end, when we want to solve a problem, then we have to observe, we have to make a measurement, we have to look at our system. And when we look at the system, quantum physics tells us that all the superpositions disappear and only one appears randomly. So if we just create these superpositions and do the computation just in these different superpositions at the same time in parallel, and then look at the end, then if we don't have any advantage of having these superpositions because we will single out one of them and the other one is as if they had not existed. And that's why in quantum computation and also in quantum simulation, what is important is to use the laws of physics to exploit the superpositions during the computation, and at the very end, to get rid of the superpositions, following the laws of quantum physics such a way that the result at the end, there is no superposition anymore, and is the result. And this is very difficult. One has to think how to do that in practice, and this is why we have very few applications, because people have only figured out for problems related to cryptography, for optimization, what I mentioned before, how you can use these superpositions in the middle, but at the end, get rid of these superpositions in a controlled way. And so it's more about interference. It's a phenomenon in quantum physics rather than only superpositions. Okay, so now these superpositions not only appear in quantum computation, but they also appear in many aspects in science. So when we study physics or chemistry, then you will have to study quantum physics, and then these superpositions become important. So in fact, if you have a chemical compound, we have a material, or if you study high energy physics, then it turns out that you are confronting to these superpositions. So you want to describe how this material will behave or what will be happening during a chemical reaction, then there will be these superpositions. And in fact, this superposition, this property of quantum physics, gives rise to very exotic physical properties. So for example, materials can be superconducting, that they don't consume energy, let's say, and this is due to these superpositions. Or you can have topological phases of matter. You can have things related to the Standard Model. You can have chemical reactions. In all of them, these superpositions are very important. And so the fact that quantum physics is behind, it's very important to understand or to design products based on materials or based on chemistry. However, if we want to study them now, let's say with computers, we want to predict the properties of materials or predict the properties of chemical reactions, then we will have to deal with the superpositions. And so this means that you will have a computer that should be able to do computation, this 2 to the power n computation at the same time. So you want to describe a problem with 20 electrons, then you will probably have to use a computer that has a capability of a memory that has 2 to the 20, let's say, bits. If you want to have now 300 electrons and you want to describe what will be the behavior, then you will have to have a computer, like a classical computer, a supercomputer, have a memory which scales like 2 to the power 300. And 2 to the power 300 is such a big number, it's like 10 to the power 8, it's like 1, 1, and 80 zeros, that it will be impossible just to do that. So you see that the quantum physics and the existence of superpositions, on the one hand, make it very difficult to study materials, to study chemical reactions, to do scientific research. And on the other hand, it helps us to solve some other problems through quantum computers. It's the same reason what is behind. So very soon, I mean, in the 80s already, Richard Feynman realized of this fact and said, why don't we use quantum computers to solve problems in material science or in chemistry? And that's what is the field of quantum simulation about, is to use, as Richard Feynman wrote in '81, is just to use quantum computers to solve what we call technically quantum many-body problems, the one that appear in material science, high-energy physics, or chemistry, for example. And so the idea is that you want to solve a problem instead of trying to put all the information about the superpositions in a standard computer, then you use a quantum computer. In the quantum computer, you create the superposition. So you want to study n electrons, you have n qubits, and only n qubits, not 2 to the power n, and then solve with a quantum computer and make the predictions to that. So this is why the problem of quantum simulation is very natural for quantum computers. It's where we know very well that quantum computers have an extraordinary advantage with respect to classical computers. And this is what I want to talk about. So now that we know that, in principle, we can solve problems in science using quantum computers, so how do we do that? And the way that we do it in science or in technology is that we need algorithms. We have to run some program in our computer in order to solve the problem that we want to solve. And so people have been devising algorithms, quantum algorithms, that will run on quantum computers in order to solve these problems that appear in physics, chemistry, and so on. And I just want to mention some of them because they already show that there is a big advantage already at the algorithmic level from quantum computers as compared to classical computers. So now it gets a little bit more technical. So one of the problems that you would like to solve in these many-body problems is the problem of dynamics. So you would like to start with your material or your chemical compounds in some situation. You would like to shake it, and you would like to predict how it will behave in the future. There will be a reaction. Will there be conductivity? Will be a magnetic material or not? So that's what we call a problem of dynamics. And it's defined in the way that you're giving some, we call it an initial state. This is the initial situation of your system. And then you're describing, or you know how particles interact with each other. So physicists, I mean, it's something that we have a very strong knowledge about that. And what you want to do is to predict what will happen in the future. You have to run the movie to know what will happen in the future, and you're interested in computing some physical quantity. That's this O that appears in the middle of this formula. And in fact, already for more than 20 years, we know an algorithm that can solve this particular problem. This was developed first by Seth Lloyd in 1996. And the idea is very simple. Just follow the recipe that Feynman told us. Just take your quantum computer, prepare it in the initial state that you want to solve, then apply some quantum gates which will evolve the state of your quantum computer in the way that the system that you want to study will evolve. And at the end, just measure in your quantum computer the quantity that you would like to predict, repeat it many times, and with that, you will have statistical information to solve this problem. In fact, with time, so people were able to improve this algorithm, and we know that the computational time to solve this problem just scales with the number of particles that you have in your system, and it's with the time that you want to simulate, and with the logarithm of 1 divided by the prescribed error that you have. And then you have to compare this with the best algorithm in a classical computer. The best algorithm, if you don't use a quantum computer, scales exponentially with n. So here's where we have an exponential advantage. In other words, you have 300 electrons, and you solve it with a quantum computer. It may take 300 units of time in your quantum computer. If you solve it in a classical computer, it would take 2 to the power 300, which is millions and millions and millions of years, which will be more than the age of the universe. So that's a very clear case where we know that quantum computers can help us. Now, the second problem is the study of equilibrium properties. No, we will not like to know what is the dynamics, but we will now to know what happens with this material. We cool it down to very low temperatures. So it turns out that some of the exotic properties, like superconductivity, occur at very low temperatures, and we would like to make predictions about what happens. That's what we call equilibrium at 0 temperature. And the goal is now, in technical words, if somebody tells us what are the interactions in the system, that's something that we know very well, like physics and chemistry. And then to know what happens at 0 temperature, we have to compute also some formula. And for that, it turns out that it was shown already many years ago that this problem in full generality is difficult even for quantum computers. So you take this problem, you want to solve it, and you don't make any specification. You say, well, these electrons will interact in some particular way, which is not the real one. Then this would take even an exponential time with a quantum computer. That's what this complexity diagram shows, that this is what is called a QMA hard problem. However, what we also know is that there are some other algorithms that have been created, in particular what is called the adiabatic algorithm, which is heuristic, meaning that it will not work for all problems, so it will not work if you just specify some interactions that are completely crazy. However, for the interactions that appear in nature, then we understand very well that this adiabatic algorithm works and finds a solution also in a time that only scales linearly or quadratically with the size of your system. And well, I wanted to talk a little bit about how this algorithm works, but I will spare you this description. Now, another problem is you like to know what happens not at 0 temperature, very, very low temperatures, but what happens if you heat it up, your system. So you increase a little bit the temperature, how the properties changes. Because, for example, you want to design some superconductor, and you cannot cool all the way to 0 temperature. This is very, very expensive. You would like to know if you go to more higher temperature, which is when it doesn't cost so much to cool at that temperature, whether these properties persist. And indeed, this problem is also very difficult. So you would consider problems that are not physical, so problems that would obey laws that you would invent. Then there's a very difficult problem. It's also what is called QMA hard. However, again, if you consider problems as they appear in physics, like problems related to materials or to high energy physics, then it turns out that there is some scale of temperatures at which you can solve them efficiently with quantum computers, whereas with classical computers, they will take an exponential time. So that's what is, use it here. So that is what is expressed here by this diagram. So, and you have a quantum computer, then you will be able to solve the problem all the way up to 0 temperature. However, with classical computers, we only know how to solve these problems efficiently at sufficiently high temperatures. And then there is a temperature in which many of these problems are very difficult. So there is a broad range of temperatures in which quantum computers will also help. So a couple of years ago, we came up with an algorithm that shows that this is possible, and this is the one that is announced here. So altogether, so far, the message, indeed, if we have a quantum computer, a perfect quantum computer, then we would be able to solve problems that are important in science and maybe also in pharmaceutical design and some other things that we will not be able to solve with classical computers. There is a big advantage, and we understand it very well. And the reason behind is what I told you. In order to solve these problems, then you have to deal with quantum physics. You will have to deal with superpositions, and the superpositions are very unnatural for classical computers and very natural for quantum computers, and this is where the advantage comes from. Now, well, what about devices? So now we know the algorithms, we'll have to put in a device and run it. So do we have these devices ready? And so it turns out that what I told you before is true if we had scalable quantum computers, not small prototypes. And so one question is, so what happens until we build these quantum scalable quantum computers? We can still get some advantage. And so there are two scenarios that people are looking at. One is what is called the NISQ scenarios. It's noise intermediate scale. So these would be small quantum computers like the ones that I showed you before that still have errors. Okay, so that whenever they have to do something with these quantum bits, then they don't create the right superposition. They create a little bit wrong, the superposition. And actually, the second scenario is not a quantum computer, or it's not like a quantum computer. It's more like an analog computer. So maybe some of you heard that in the 20s and the 30s of the last century, before they created the first digital computers, there were analog computers. And in the same way, so we are building quantum analog computers that they don't work like with a clock, just stepwise, digitalized, but continuously. And it turns out that for some of these problems in quantum simulation, or to solve these problems that I mentioned before, these analog computers already, even if they are not perfect, then they're very powerful, even more powerful than some of the quantum computers that are digital. So I want to talk a little bit about that now. And so there are many technologies. It was mentioned before that there is many platforms in which people are trying to build quantum computers and dedicated quantum computers to solve these particular problems in science that I mentioned before. And so you have technologies based on trap ions. You have technologies based on superconducting qubits, so into trap ions, superconducting qubits, and you have also Rydberg atoms or atoms in optical lattices. And in all the three of them, then the qubits are stored in the way that I told you before. If you have ions, it would be like in the properties of the magnet, being North Pole up or North Pole down. These are where the quantum states are stored. In the case of superconducting qubit, is in whether the current runs clockwise or counterclockwise. But you also have some other technology, photonics, in which it's in some properties of the photons that are moving in the circuit, where you have these quantum superpositions, quantum dots, also NV crystals. So all of them, have been mentioned here, or most of them have been mentioned before. And these are the different running horses that we have, not only for quantum computation, but also for quantum simulation. It's not clear what is the winning horse yet, and that's why it was mentioned before that now we are planting all of them and seeing what is happening. So what it seems at the moment, the one that is like taking the lead in the quantum simulation is the one based on cold atoms in optical lattices. This doesn't mean that this will be forever. It may happen that the superconductors or the quantum dots or the photons take over after some time, but I just want to concentrate a little bit on these cold atoms in optical lattice. And so this is a system that will implement one analog quantum simulator. So the idea here is not to create a digital quantum computer, but to work in the analog way, as I mentioned before. And so what you do is that you put some laser fields, and these laser fields will create some interference pattern. And so what it means in practice is that the intensity of the field just oscillates. It's very high, very low, very high, very low, very high, very low, very high, very low, with a periodic structure. And now the atoms that are like the small, call them dipoles, then they get attracted to the places where there is maximum intensity. So if there is an intensity, then they will be there. And if now there is a very low intensity, they are not there. If there is intensity, they are here. And so you see that the atoms will be trapped in a periodic structure, just as if it's described in this diagram, which is here. And now the atoms can hop from one of these, we call potential wells, to the next one, and then move in the same way as electrons move in materials. And in fact, this is the right analogy, because this was proposed to simulate the motion of electrons in materials. And it's very natural, because these atoms would move in the same way and following the same laws like the electrons in materials. So that's one of the quantum simulations. And now, in the last years, so many groups, and in particular my group, have been working on different problems that could be solved with this particular quantum analog simulation. So problems in the field of condensed matter physics. This was together with Peter Zoller, like many of the works that I did in the past. So problems in quantum optics, problems in high energy physics, and in the last couple of years, we have studied how to solve problems in chemistry just using analog quantum simulation. And just to mention the one on quantum chemistry, so the idea there is if you have a problem in chemistry, then probably you know that in chemistry you have nuclei, and then you have electrons, and the electrons are attracted to the nuclei, and the nuclei repel themselves, and the electrons repel themselves. And so one of the things that you would like to know is, since the nuclei are very heavy, then to say, what happens if I fix the position of the nuclei, and now study how the electrons would move in these positions of the nuclei, and in particular, what would be the state in equilibrium as a function of the position of the nuclei. And so what you can do is now to take these atoms that move from the lattice, then put some lasers that play the roles of the nuclei so that the atoms will be attracted to the positions where these lasers are. And on the other hand, the atoms, they have to behave like electrons, so we'll have to repel. However, these atoms, actually, they are neutral, so they repel, and that's where, the difficult part comes. So how do you make atoms to repel each other? Some atoms that are neutral, they are not charged, to repel each other, even if it are a long distance. And in order to do that, so the idea that we were developing is to imitate nature. So if you study quantum physics, quantum electrodynamics, then you know that when you have electrons, the fact that they repel each other is because they exchange light. So one electron, like I'm an electron, I emit a photon, and then I'm pushed back, because the recoil. And then if there is another electron that is here and absorbs the photon, then it gets another recoil. So altogether, we are like pushed apart, and that's the mechanism that gives rise to the repulsion. So you can simulate the same thing, the same behavior, just using some other atoms that will play the role of these photons, and then therefore you get the right simulation. And so that's just one particular place, but this opens up the possibility of doing now quantum simulation, not only in physics, but also in chemistry. The experiments are extremely difficult, so probably as difficult as to build a quantum computer themselves, but anyway, so that's a proof of principle that this works. Now, so what is the experimental situation? These were theoretical ideas, so what happened in practice? So one can, I think, claim that the first quantum simulation was done in the year 2002. This was in the group of Emmanuel Bloch, who's a member of my institute, actually. And so they observed this transition between two states of matter in some particular simulated way. And now let me finish up with some other experiments that occurred in the last couple of years, or 5 years or so. And so one experiment, for example, was doing a simulation of the dynamics of some particular model describing photons in materials. And so as you can see, the experiments are the dots that you can see as a function of time, which is the horizontal axis. And what they claim at that time is that the theory that was done with a classical computer could follow the experiment, but not all the way until the end. So this meant that already with that system, they were able to do something, an experiment which was very difficult to replicate with classical computers. Another experiment which was performed at Harvard with cold atoms as well, and they were just playing and trying to do some simulations, and actually they discovered some phenomenon. And they discovered what is called scars. So what they saw is, so you expect that if you have like many atoms, many electrons, and then you will shake a little bit, then it will oscillate, but at the end it will decay, and then the oscillations disappear. And what they observed is that they didn't disappear. They stayed for very long, and they discovered an effect. So this was used to discover an effect. And the third one was a couple of months ago, in which it was claimed that the first utility of quantum computers was used in fault tolerance. So they were saying that they had a quantum simulation that was difficult to replicate with a classical computer. However, when the day of the publication, then 3 papers came out and find how with a classical computer they could reproduce the results. So this means that in quantum simulation, like in quantum computation, you have to be very careful when you make claims that you have quantum supremacy, because you have to make sure the next day somebody will not come with a classical computer and will be able to solve it. So with that, see that my time is up, so I'll go to the conclusions. So we just enter, let's say, this prototype era of quantum computations, but still scalable quantum computer where we know very well what are the applications, still many years to come. Quantum simulation seems something that is at reach, and that even, didn't have time to mention that, even if we have some errors, if the simulators are not perfect, they still can provide advantage with respect to classical computers and in problems that are relevant, at least in science. And the other one is that probably the most important applications are to be discovered. So thank you for your attention.
So thank you very much, Ina. So your talk asked a lot of questions about the respective possibility roles of simulator, computers, etc. We'll keep these questions for the end of the session. So we'll move now to the second speaker, so Serge Haroche. So Serge Haroche is a French physicist. He holds the prestigious chair of quantum physics at the Collège de France in Paris. He obtained his PhD in 1971 under the direction of Claude Cohen-Tanucci, a Nobel Prize. Then he has been a professor in many institutions, including the MIT, Harvard, Yale University, at the University Pierre et Marie Curie in Paris. He was also head of the physics department at the École Normale Supérieure and administrator of the Collège de France. So his main research subject for many years has been Rydberg atoms, giant atomic states, which are particularly sensitive to the electromagnetic radiation. This makes them well suited for studying the interaction between light and matter. He shows that such atoms, Rydberg atoms, coupled to a superconducting cavity containing a few photons, can be used to realize a lot of extremely important experiments, demonstration experiments on quantum measurement, on quantum gates, and also for studying quantum decoherence. His pioneering work gave rise to a full research field, which is called cavity quantum electrodynamics, cavity QED, which has many applications in quantum technologies. Serge is also an exceptional teacher, and he wrote a book recently, which is called in French, La Lumière Révélée, which is a broad audience book, so, and it was translated in English, in Spanish, and even in Chinese. So I encourage you to read it. So for his work, he got many national and international awards. On the French side, he is Grand Officier de la Légion d'honneur. He obtained the gold medal of CNRS. And most famously, in 2012, he was awarded the Nobel Prize for Physics, jointly with Dave Wineland in the US, for groundbreaking experimental methods that enable measuring and manipulating individual quantum systems. Serge, the floor is yours.
I don't know if my mic is working. Can you hear me? Maybe I will, yes, okay. So thank you very much for the kind introduction.
So we have learned from the previous speeches and from the introductions that quantum technologies and in general quantum information science is developing very fast in many labs throughout the world. I was told that in this audience we'll have a mix of people. Some people are scientists, others are policymakers and are not specialized in science. So I'll try to come back to very basic things which will make my talk overlap with what Ignacio has said. At least in the first part of the talk, I will repeat some of the things he has said, but in a different way. I want first to recall that we are now talking about the second quantum revolution, but we have to remember that quantum physics have given rise to all the devices that we use today in our everyday life, whether it is the classical computer who works because we know how transistors work and we have quantum effect in that. We know that lasers are based on the knowledge of the quantum interaction of atoms with photons. We know that the GPS, atomic clocks, and so on, and I could multiply the example, are working according to these principles. And an important, interesting thing to say is that when quantum physics was discovered, and as that it has been recalled exactly 100 years ago when Louis de Broglie discovered the wave nature of matter, nobody talked about quantum revolutions. They just did it, but they were not even thinking that they were in the middle of a quantum revolution. So maybe now what we are thinking about the future is not at all what will happen. We have to do some basic science and we'll see what will be the outcome. So I will try to convey these ideas, but first I would like to recall briefly what Ignacio said, that quantum physics is based on the principle of quantum superposition, the fact that a system can be suspended between different classical realities. For example, electrons in going around an atom, the nucleus of an atom, are in a superposition of a huge number of position states. In fact, a continuous number of position states. The wave function is a state superposition. A photon can be in a superposition of states with different polarizations. An atom can be in a superposition of states with different energies. This was also discussed by Ignacio. And in this superposition, the weight of each component in the superposition is a complex number, a complex probability amplitude. A complex number is richer than a classical number. It's a number which has an amplitude and a phase. And when in a superposition, a very important phenomenon occurs when you can combine different states of the superposition and get interference effects, quantum interference effects. And this is really the basis and the heart of all these phenomena. So in the next slide, I have tried to, if the movie works, to show you a very simple quantum interference effect, which is the Young double-slit experiment, an experiment in which you have a source of single particles which follow two different trajectories, classical trajectories, to be detected on a screen. And you see here the screen and how the experiment works. It's not. I'll try to get the movie working, but for that I have to get here. Yeah, you see that progressively, as particles are crossing the apparatus one by one, progressively you have an interference pattern which happens. And this interference is due to the fact that at some positions, the two passes interfere destructively and other position positively. And since this happened with particles crossing the system one at a time, it means that each particle, each photon electron in this experiment is in a superposition of two states. So these are two states corresponding to different trajectories. An atomic qubit is something similar. It's a superposition of two energy or two spin states. As you can see here, you have a ground state and an excited state, which can be a spin down or a spin up, as Ignacio described. And you can put these atoms in a state superposition, starting from the atom in the ground state, by shining on the atom a pulse of light, laser light, or a microwave pulse, if these are two close space spin states, and by tailoring the pulse, giving it the right duration, and the right amplitude, you can create any kind of superposition between the two states. And this is called a quantum bit, as Ignacio mentioned. It codes a bit of information, and instead of using the plus and minus notation, you can call one of the states 0, the other 1. And you get now a quantum bit, a bit which has much more contains much more information than a classical bit which has to be either 0 or 1. Here you are in a superposition, and this is the wealth of this situation. It gives you much larger space to explore if you have several bits interacting with each other. But this richness has a price, and the price is that these superpositions are very fragile, and that when you make a measurement, you get only one result. And this is a measurement problem. I cannot describe this problem in details, but just to give you an idea, I take again the case of the double slit experiment. If you ask yourself the question, through which slit the particle went, for that you have to observe the particle, so you have to modify the setup and to use, for example, a lamp which sends photons on the system, and then you look at the light which is scattered by the particle, and you will observe whether the particle crosses through one slit or the other. But in order to do that, you have to apply light of short enough wavelengths to get an optical resolution, and this short wavelength light carries a lot of momentum, and this will perturb the trajectory of the system so that you will lose the interference. You will not be able anymore to see this interference due to the succession of positive and negative interference phases. So the system is perturbed in a way which you cannot avoid, and moreover, the result that you obtain will be randomly observing the system in the left or in the right part. So it means that, in fact, nature obeys to this law of chance. As Einstein said, God is playing dice in quantum physics, and you have to take this into account. It means, as has already been noticed, that if you want to do an experiment, you have to not to observe anything, to keep the experiment, so to speak, in the dark, to let all the superposition build up, and in the end, at the right time and the right condition, perform a measurement which will give you the information you need. This would be perfect if you do not have someone else who is always spying on the system, which is the environment. And this is a problem of decoherence that I would like to mention briefly. What happens, in fact, is that even if you don't like to look, even if you leave the system in the dark, you have a lot of, even at the best, lowest possible pressure, you have random photons, you have a background gas in the system. Even if you try to go at the lowest possible temperature, you have black body radiation. Even if you want to make sure that nothing moves in the system, you have vibration, you have photons, and all this interact with the system, and this environment plays a role of a measuring device. Some information is leaking out of the system, and very quickly, the particle in this case is obliged to choose whether it is on the left or on the right. This is a phenomenon of decoherence, which explains why, at the macroscopic scale, we never see a quantum superposition of two big objects, because if the object becomes large, these effects become very, very efficient. So, in fact, it explains why the classical world, the macroscopic world appears to be classical, but it is also a big challenge for quantum information, especially for quantum computers. And I will come back to this in a moment. So now, let's look at what happens if you couple two qubits with each other, two bits like that, and you look, first of all, you put the two qubits at a very large distance from each other so that they don't interact. What are the energy levels? If the two particles are, for example, spin down, you get one energy level, and if the two are spin up, you get much more energy. And then you have an intermediate state in which one spin is up and the other down, which is just midway between the upper and the lower state. And you see that this intermediate level, in fact, has two possibilities. Either the first spin is up and the second down, or the opposite. And these two states have the same energy, of course, if the system don't interact. Now, let's bring the two qubits together. It's called a resonant coupling, because when they exchange their state, the energy is conserved, obviously. And a basic law of quantum physics is that when you have this kind of possible resonant exchange between the two qubits, the degeneracy of the level is lifted, and you have one state which has an energy higher and one state which has an energy lower, which are respectively the positive, the symmetric and antisymmetric superposition of spin up, spin down, plus or minus spin up, spin down, spin up. This resonance phenomenon is something which happens everywhere in quantum physics. And for example, if you have two atoms, it explains that the two atoms get attracted to each other because they go into the lower state. And this is the basis of molecular binding, for example. But here we have this problem. And now you can ask yourself the question, what will happen if you start with one spin up and one spin down? And you see that, in fact, the system is in a superposition of the two states, the two energy states, with a symmetric and antisymmetric superposition. And again, you have a situation which is similar to the one we have with the Young double slit. You will have an amplitude which will have a phase which will evolve differently whether you are in the up or down state. And if you wait some time, the probability to find the system in the down-up state, if you started from the up-down, will oscillate in time as a result of a quantum interference. And this oscillation in time is quite analogous and mathematically equivalent to the oscillation in space that you had in the Young double slit experiment. So you see what will happen is that the system will evolve in a superposition of spin up, spin down, plus spin down, spin up. And this superposition will evolve at a rate which is the energy difference between the two levels divided by the Planck's constant. And omega, this frequency, is called the Rabi frequency in the system. So you get an oscillation, and you see that if you stop at a time corresponding to 1/4 or 3/4 of a period, you have a system which is superposition in which the amplitudes to be in one state or the other are exactly the same with a plus or minus sign. These states are said to be entangled, and they have very interesting properties, which I will try to discuss on the next slide. So let's look at what we have done. We have started from spin up, spin down, two independent spin, and we get this entangled state after having let them exchange during the right time. Then you can do something else. You can now act only on the first spin. It's a single qubit operation. You can flip the first spin without touching the other one. For example, you can focus a laser beam on the first spin, and this laser beam does not act on the second one. And you see immediately that the red spin will go down on the left, and will go up on the right part, and you get now another state, which is spin down, plus or minus spin up, spin up. So you see that with this very simple operation, you have been able to generate 4 states which are maximally entangled. These are called Bell states. What does it mean that they are entangled? It means essentially that you cannot consider what happens to one spin without looking at the other. In particular, if you make a measurement, you will find that the spins will always be correlated. And this not only if you measure them in one direction, but if you try to measure them in any other direction, which means that if you make a rotation on each spin and make a measurement after that, you will find the same kind of correlation. What is important to notice here is that there is no information in each spin independently of the other. The probability to find the first spin up or down is 1/2 always. The probability to find the other spin up or down is also 1/2, which means that you have no information there. All the information is counted in the correlations between the spins. If you find one spin in one direction, you know for sure that the other will be in related direction. So measuring one qubit collapses the state of the other at a distance in a mirror superposition. This is an effect that Einstein called a kind of spooky action at distance, and it is, of course, the basis of quantum cryptography, which would be the topic of Anton Zeidinger's talk. So I will not discuss it anymore here. And I just want to go on with the possibility to build a quantum computer. What I have tried to show you is that combining qubit spin exchange with single qubit operations realize a quantum gate. What is a quantum gate? It's a gate in which one qubit, the state of one qubit, controls what happens on the other. The first qubit is called the control, the other is called the target, and you can choose all kinds of possible gates in which the control will make the target do something or something else. And a very important gate of this kind is called the keynote gate, in which the control qubit decide whether the target bit flips or not. If the control is in state 0, nothing happens to the target. If the control is in state 1, the target goes from 0 to 1 or from 1 to 0. This gate is, and of course another important point here is that the control never changes. The control stays stable, but just decides what happens to the target. If you go now to state superposition, you see immediately that if the control is in a superposition of two states, the result will be an entangled state. So this kind of gate can be used to entangle or conversely to disentangle two qubits. And this is the basis of what would be a universal quantum computer. If you can have a huge number, as Chirag Ignacio described, you can combine a huge number of such qubits, you would be able, starting for any initial state, to reach any superposition of a huge number of qubits, provided, of course, that all the operations run perfectly well and provided that you are able to avoid decoherence in the system. And this is the big if. The question which is open is whether you have enough resources realistically to achieve this goal, and I think we will certainly have this discussion in the panel session. So as I will go very fast here because Ignacio again described all these qubit candidates, cold atom or trapped ions, or photons in nonlinear media, NV centers in diamond, quantum dots, superconducting qubits, polaritons in quantum wells and the Bragg layers of semiconductors, and another field, which is a field in which I have been working, which is Rydberg atoms in cavities or Rydberg atoms interacting with each other. And I will spend the second part of the talk discussing what we can do with these Rydberg atoms. In fact, a Rydberg atom is an atom in which laser excitation has brought an outer electron to a very large orbit. And when I say large, it's indeed very large. You can have atoms in which the size of the orbit is thousands of times bigger, hundreds of thousands of times bigger than it is in the ground state. We are working with states with the principal quantum number equal to 50, and the size of the atom increases as n squared. That is, the atom is 2,500 times bigger, which means that the atom has the size of a micron, size of a virus or a bacteria. These atoms are very fragile, which means that they are very sensitive to interactions with other systems, for example, with microwave photons or with other Rydberg atoms. And in the context of our discussion, I will consider a situation in which the Rydberg atom can evolve between two neighboring Rydberg states. So one state would code for a qubit in state 1, and the other will be the qubit in state 0. And these two levels are in fact connected by microwave transition. So these atoms will be able to exchange microwave photons with a field contained in a cavity. And this is the kind of experiment that we have been working on for many, many years. And I just show you here the principle of the experiment. We have a very good cavity, which is made of superconducting mirrors, in which photons can be trapped for a long time. And Rydberg atoms cross the cavity one at a time, and they interact with the field in the cavity. If the cavity is exactly resonant with the atom, we get the situation of the Rabi oscillation I described before. Instead of having two spin states which exchange each other, now we have one spin, which is a Rydberg atom, and the other one is the photon state, which in the simplest case corresponds to 0 or 1 photon. So you again have a flip-flop situation, and you see indeed that you can, in fact, record a large number of Rabi oscillations. So you have a periodic exchange. In the most general case, if you stop the interaction at a given time, you are in a superposition of E0 and G1, which means that even after the atom has left the cavity, you have an entanglement between the field in the cavity and the atom which has escaped from the cavity. And you can observe and measure this entanglement. When you measure the atom, you project immediately the state of the field in the mirror state, and so you can play with that. You can send another atom to the first one and entangle atoms together. And of course, as I tried to show you before, this is equivalent to building quantum gates in which one qubit is the atom, the other qubit is the field. The field has many more possibilities because a field is made of equivalent. Okay. Another interesting situation occurs if you detune slightly the atom of the cavity. Then the Rabi oscillation cannot happen because you don't conserve the energy. But what happens is that the two systems shift their energy levels a little bit. For example, if you have one photon in the cavity, the upper energy state will be slightly have a slightly higher energy, and the lower state is slightly lower energy. This is called a light shift, but it's a light shift which is induced by a single photon. And what you see is that if the atom interact during time t in the cavity, you get a phase shift of the atomic superposition, which is equal to omega squared t over delta, where delta is a detuning between the atom and the cavity field. And this has led us to realize an experiment which is schematized here, in which we use this phase shift effect to determine whether or not we have a photon in the cavity without absorbing the photon. The principle of the experiment is called the separated field Ramsey interferometer. You apply first pulse of the atom before it crosses the cavity, so you prepare the atom in a superposition of two states. Then you let the phase of the two states evolve, and a second pulse will lead you to a measurement. And what you find is that if you adjust the system so that you get a pi phase shift per photon, the atom prepared in one state will end up in the other state if there is one photon, and will stay in that state if there is zero photon. This is again a quantum interference, and it is a kind of quantum interference that you get in all atomic clocks. In fact, this Ramsey design is used in the standard microwave clocks of the GPS system, but here we look at how the clock is perturbed when you have one microwave photon inside the space between the two Ramsey zones. So we have done that. And again, this is something which looks like a quantum gate. One photon in the cavity determines whether the atom will end up in one state or the other. And you see how it works here. Here you have zero photon, so the atom gets out in the up or down blue state. And then when one photon appears in the cavity, the system jumps to the other state, and then when the photon disappears, it goes down. So you see quantum jumps, and you also see that hundreds of atoms crossing the cavity one by one see the photon without destroying it, which is quite different from the photoelectric effect in which in fact had been explained by Einstein, and this was the motivation for his Nobel Prize. In the photoelectric effect, when you detect the photon is dead. It is replaced by an electron. Here, the photon stays in the cavity because we use this subtle technique to extract information from the system without destroying the photon. And by the way, if you set up the system in this way, and if you have more photon in the cavity, what happens is that you are in fact measuring the parity of the photon number state. Because if you have a pi phase shift for one photon, it means that you will have a 3 pi phase shift for 3 photons, a 5 pi phase shift for 5 photons, and the atom will always end up in the same state. On the other hand, if the photon number is even, the atom will go in the other state. So it's a parity measurement of the photon number, a non-destructive measurement of the parity of the photon number, and as I will show you in a moment, it's very important for some application in quantum information. Here I have described what happens when one photon controls the state of the atom. Now you can do the opposite. You can see what happens if one atom controls the state of the field. And this is the experiment described here. We start by feeding the cavity with a classical field. A classical field is a field which has an amplitude and a phase, and you can represent it by an arrow in a plane, which is the way I have shown it here. And then you send one atom across the cavity, and before the atom crosses the cavity, you prepare it in a superposition of two states. The atom is non-resonant with the cavity, but it will shift the frequency of the cavity field. This is the effect, the mirror effect of the one I described before. In the first experiment, the photon was shifting the atomic frequencies, and here it's the atom which shifts the field frequency. But since the atom is in a state superposition, what you see is that now you will have an entanglement. The state of the atom will be correlated to the phase of the field, and this state is entangled. What you do on the atom will have an effect on what happens to the field. The clever way to do the experiment is to mix again the two states after the atom has left the cavity, and then if you detect the atom, you project the field into a quantum superposition of the two phases. This is what is called a Schrödinger cat of radiation. It's a system which can contain many photons, up to a few tens of photons, which is in superposition of having one phase or the other. Then you can add a field which will cancel one component and double the other one, and you will have the very strange situation of a cavity which has either the vacuum or a large number of photons at the same time with a quantum interference between the two possibilities. This situation is very similar to the famous Schrödinger cat tale, in which he considered the situation in which an atom in a state superposition will control the fate of a cat, killing the cat in one state and leaving the cat alive in the other one. And of course, nobody observed this situation, and one part of the explanation, at least, is decoherence. The cat contains a huge number of photons, a huge number of atoms and molecules, and the decoherence becomes very fast. In fact, before you have time to prepare the system, the cat is no longer, the cat has never been in a pure quantum state. It has always been mixed with the environment, and so you cannot do this experiment. So this is a paradox, and the big question which relates to the question of the quantum computer is how big can a system be maintained in a state superposition? And we have been able to study this problem experimentally by just increasing the number of photons in our Schrödinger cat situation. So we represent this representation here is called a Wigner function. In the 2-dimension, you can, in each point of the complex plane, have a number which represents the amplitude of the field. And you see that this Wigner function presents two peaks which are equivalent to the dead and the cat state situation. And you see that between the two peaks, you have a quantum interference, which is a signature of the fact that these two states are in a quantum coherent superposition. So we have been measuring these Wigner functions and looking at what happens to them if you let them stay in the cavity for some time and increase the time. Unfortunately, this is not my computer, and the movies that I have tried to show, that I will try to show, I think will not work on this. Let me try again. In fact, we should have a movie here which does not work, but what happens is that the quantum interference that you see between the two big Gaussian peaks vanishes very quickly. The two peaks stay there, which means that the cavity has not lost its energy, but the quantum interference is washed out very quickly because of decoherence. And I wanted, this is a work for which, go back. This is a work for which a Nobel Prize has been awarded 11 years ago, and I want to take this opportunity to just recognize my co-workers, Jean-Michel Raymond and Michel Boyne, with whom I have been working for many, many years. And the experiments about the quantum measurement of photons and quantum decoherence has been performed by very bright graduate students and postdocs, Dotsenko, Glaze, and Serrin, who have gone on working on this kind of problems and are now PIs doing very nice work independently. So before going to the last part of the talk, I want to make a comment about the Schrödinger cats. In fact, you can prepare either the plus or the minus superposition of two states of opposite phases. The only difference between these two states is the fact that the quantum interference in between is shifted by half a fringe. And if you look at what happens, you have again a quantum interference. In the even cat, which is a positive superposition, the quantum amplitude to have odd number of photons cancels. And so it's an even state. It's a state which contains 0, 2, 4, 6 photons, but never 1, 3, or 5. On the other hand, the other is an odd cat state, which has only odd photon numbers. And what happens when decoherence occurs? Decoherence is a loss of one photon. So it means that if you start from the even cat, as soon as one photon is lost, it becomes an odd cat. And then the next step would be again be an even cat. And so you see that the loss of coherence is due to the fact that these quantum jumps happen at random time, that you cannot control them. But now we have a way to control them, because you can combine this experiment with an auxiliary atom, which would measure by the quantum non-demolition procedures I described before, the parity of the photon number. So each time a decoherence process would occur, the parity would change, and the system would be again will have the other parity. And then you can correct this, and I don't have time. This is an excuse I'm taking because I could not describe even if I had time. But what you can do, is, in fact, preserve for a longer time the coherence of the system. This does not happen in cavity QED. The defect of cavity QED at this stage is the fact that we have flying qubits. The qubits are crossing the cavity and are lost. In circuit QED, which is a superconducting system that Ignacio mentioned, you have artificial atoms which are coupled to cavities, and these artificial atoms, of course, do not move, and you can do the same kind of experiment with this system. The advantage is also that these atoms are big. They are even much bigger than Rydberg atoms, and the coupling to microwaves is much stronger, so everything goes faster, and you can do then this kind of bosonic error correction codes. And just for aesthetic reasons, I show you the kind of 2, 3, and 4 Schrödinger cat components which are being studied in this domain. I will need 2 or 3 minutes to conclude. At this stage, it seemed that circuit QED was taking advantage over atoms. But since then, a lot of progress has been made. Again, as Ignacio mentioned, cold atoms in optical lattices are now back at the front of the stage, in particular with Rydberg atoms. Now you can, instead of having a Rydberg atom interacting with the cavity, you can have 2 Rydberg atoms interacting with each other, and you have the same situation of quantum resonance that I described before. If an atom is in the level n, level n-1, you have a resonant exchange between the two, and you have a flip-flop, which again allows you to entangle the atoms. And you have another very good qubit candidate. And now I think I can have 1 or 2 more minutes because I'm describing an experiment that you did. So there is a very interesting effect which is called the Rydberg blockade, and which gave again a great put the focus on Rydberg atoms again at the beginning of the 21st century. You can use optical tweezers, that is, focus a light at 2 very close points in order to trap a single atom in each of these traps. And this is a kind of experiment that our dear chairman has pioneered at the beginning of the years 2000, using single tweezers to bring atoms at a well-defined distance. And then you have a very interesting phenomenon which is called the Rydberg blockade. If you shine a laser beam on these 2 atoms, you can easily excite a first atom into Rydberg state. But once the first atom has been excited, because the energy levels are shifted by this excitation, the second atom will not be excited. And so you introduce some fundamental nonlinearity in the system, which explains that what you get, in fact, is an entangled state in which one atom is excited and the other not, but it's a symmetric superposition because you have equal probability to excite the first or the second atom. So in a very natural way, without having to do much more, you get this collective oscillation and you get a quantum gate. And this is the reason why theorists, including Ignacio, Peter Zoller, Misha Lukin et al., have described experiments in which you could use these atoms. And just to give you an idea of the time scale, it took about 15 years between the idea and the realization now. And I just show you the last slide here, in which you can build, which shows that you can build an array of optical tweezers using spatial light modulators, which modulates, you can modulate at the focus of a laser beam a succession of traps, a kind of a structure of two-dimensional traps. If you just shine this on a cold atom beam, you will trap on one side out of two, you will randomly trap atoms. But then you can use a movable tweezer to fill the holes and to have an assembled configuration. These atoms are in the ground state. You see them by the fluorescence that they emit when you excite them with laser light. Then you can use another laser excitation to promote them to Rydberg states. And what you get is the figure at the right, in which you see that one out of two sides seems empty. In fact, it is not empty. The atom is in a Rydberg state that you cannot see. And this structure is an anti-ferromagnetic configuration. Because of the Rydberg blockade, excited atoms try to avoid each other, and the natural structure is a structure in which one atom out of two is in up or down state. These are experiments which are performed in a beautiful experiment done by Antoine Borwes at the Institut d'Optique, in which Philippe is working, so I'm taking really advantage of that. And this is a very interesting physics, which is very similar to some aspect of what was been described by Ignacio. These are not optical lattices, these are tweezer arrays, but it's very similar, except for the fact that the atoms can be kept at much larger distances from each other. And I just want to conclude, and this might introduce the discussion. I think there are a few things that I would like to say at the end. First of all, I want to say that basic curiosity-driven research remains essential. We are not yet, at least in the case of a quantum computer, to the point where it's just technological. We have already to find the way to fight decoherence in an efficient way for a very large number of particles. The second point, which is more political, this research has to benefit from open competition and emulation in the world, not only in Europe, but with other nations, and not only with Western countries, also with China, I think, because we are not at a stage where one country will be able to take a strategic advantage. I think this notion of strategic advantage is a kind of overplaying it, is a kind of estimating that we are at a point where it will give an advantage to one country over the other, I think is wrong, and we have to make sure that we can keep the boundaries open between the US and China, for instance. And finally, whether or not a full-fledged digital quantum computer will come of age, it's not only when, it's also if, and I think we will discuss that. And the rest is, of course, obvious. I think it's a field in which many, many interesting things are happening. A lot of startup companies are doing very interesting contribution, especially to the field of probe of sensing and quantum metrology. And I am sure that the big surprises will come. As you said, in 1940s, nobody knew what would be the application of the computer. And here, nobody knows what will come out of this research. Maybe not a quantum computer, but maybe other things which will surprise us even more. So thank you, and I apologize for
So thank you very much, Serge. I think we will postpone the question until the next, the sort of mini panel discussion. So we will move to the third speaker today, Anton Zeilinger, who is an Austrian physicist, professor of physics emeritus at the University of Vienna, senior scientist at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Science. So he received a doctorate also in 71, same year as Serge, yes, with a thesis of neutron interferometry under the direction of Helmut Rauch. After his habilitation, he worked at MIT, then as a professor in Vienna, then in Munich, in Innsbruck, and then he came back to Vienna, where he is now. So most of his research concerns the fundamental aspects and application of quantum entanglement, and the list of his achievements is extremely impressive. It includes quantum teleportation, quantum entanglement swapping, both in the lab and over very long distance, prediction and observation of 3 particle entangled states, the famous GHZ states, many experiments related to quantum communication, cryptography, computation. He's also very interested in the quantum physics of large objects, such as organic molecules, mechanical cantilevers, they are quantum. Last but not least, he performed over the years many tests of Bell's inequalities of increased sophistication until the so-called significant loophole-free Bell test that he achieved in Vienna in 2015. He also wrote a broad audience book, who was translated in French with the title Le bal des photons. You understand that? It's very Viennese. Okay, so for his work, he got an astonishing number of awards. I cannot quote them, but I will just quote the most prestigious one, which is that in October last year, he received the Nobel Prize in Physics jointly with Alain Aspect and John Clauser for their work involving experiments with entangled photons, establishing the violation of Bell's inequality, and pioneering quantum information science. Anton, the floor is yours.
Which one to use? I use both of them. Huh? Where's the point? There's a pointer. This one. Okay. Very fancy pointer. Okay, so I'm glad to be here. I would like to thank everyone who was involved in the organization of this and also in inviting me. I choose as the title Quantum Foundations, from curiosity to quantum information and back to curiosity. You see here a telescope. The telescope which we use for long-distance quantum communication between 2 different Canary Islands. In that case, it is between Tenerife and La Palma. If you ever go to Tenerife or La Palma, again, go up there and look at the telescopes. I guarantee you this is a very, very interesting experience. And we also use this telescope for developing and actually doing quantum communication with satellites. Yeah. I want to quote Arthur C. Clarke. He wrote the book on which the famous movie by Stanley Kubrick is built on, 2001: A Space Odyssey. And he writes, any sufficiently advanced technology is indistinguishable from magic. So if you feel that some of what we are talking about here is magic, then you are on the right boat today. That we have to point. It was already mentioned by Serge, Einstein's contribution in 1905. 1905 is 5 years after Planck has actually for the first time used the idea of quantum without ever talking about quantum particles. But Einstein said in 1905, well, maybe light is consisted of particles. And he has very good reasons, not very good abstract reasons. They have to do with the entropy of a radiation field and all this. But this is just some details. This is the only paper which Einstein himself ever called revolutionary. And he received the Nobel Prize of 1921. He got it in 1922 for that. And a point I wish to make here now is that in 1913, there's a famous letter signed by 3 Nobel Prize winners who recommend Einstein for a position, for a very good position in Berlin. And they write, in one idea he was wrong, namely the idea of particles of light. But without speculation, you cannot even in the exact scientists really make progress. And now imagine the time scale. 1913, the community thought this is nothing. And in 1922, he gets the Nobel Prize for that idea. And this is what is so great about science, that the whole community can change what they think. Just why? Just because we have an ultimate judge, and the ultimate judge is nature. If nature says, I don't work that way, then you can forget it. So it's the ultimate decision. And that is actually fantastic. Here's again the double-slit interference, which was mentioned already by Serge. I can be very brief. The 2 slits, and back there you have the interference fringes already mentioned. I would like to introduce my position when interference fringes arrive. Interference fringe, we talk about both particles going through both slits. I think this is not very good language. I think we just don't know what happens. We just don't know which slits the particles go through. We have no idea. And interference arises if and only if no path information is present anywhere in the universe, which path the particle takes. Be it on the particle, be it on the somewhere else. This is it may be by decoherence, the path went by interaction, the information was carried away, something like that. The important point is that you can reverse this information. You can actually make things recohere. You can have, when you erase the information, it could be the information on the particle or somewhere out there. If you just can erase it, then you get interference back again. So it's about information. The whole thing is about information. That, to me, is one of the most interesting things we have learned, at least I have learned. Information is the possibility to obtain knowledge about the past. It's only the possibility. It's not whether you or any observer has obtained the information. It's just a possibility, and it's a possibility that can be obtained by any observer. So there's sometimes the discussion that observation changes the quantum state, and even the mind changes the quantum state. This all is, for me, going too far. It's just a possibility of obtaining information. Now here's a double-slit interference pattern with neutrons, because I was guessing that you will show the photon part. This beautiful experiment by Roche. This is a pattern with double slits of neutrons obtained in 1983. And what you see here is the equivalence of the stripes in the maxima and minima. And the solid line is first principles quantum physics without any free parameter. So this is a great confirmation for the fact that the Schrödinger equation is linear in amplitude, which is a consequence of many of the other later paradoxes, etc., etc. And secondly, it was really obtained one particle by one particle. It's neutrons, so the neutrons came out of a nuclear reactor. In that case, it was the reactor in Grenoble in France. And basically every 2 or 3 minutes, a neutron was registered. So you have to imagine a neutron comes out of the reactor, flies along, goes through the double slit, and is registered. And when one neutron is registered, the next one to be registered is still sitting in its uranium nucleus and waiting for fission to set it free. So this is really one by one. And the interesting point is, when I gave these talks in the 80s, I was rather young. Even some senior physicists came up afterwards, and they said, it's really that way? It works one particle by one particle? And I said, didn't you believe in your theory? It's just what theory told you, you know, just a thing. And this kind of things now, this kind of fundamental experiments, that's the most simple one, led to new ideas about possible applications. This is what we are talking about here. Tommaso is a great organizer of us all. He put us all together here and so on. And these new ideas of these new experiments for possible applications have led to new ideas, new fundamental ideas. So let me go through some of the essences of my talk. I just want to keep time here. If I go one of the experiments we did years ago was with large molecules, macromolecules, buckyballs. They also, you know, they also go one by one through this double-slit assembly and see interferences. My friend Markus Arndt is now, he has taken this completely over. He's now by much larger objects in the order of 20,000, 30,000 Dalton. This is the unit of atomic mass. The other point, it has been already mentioned already, is quantum entanglement. And I cannot resist to show this paper from 1935 by Einstein, Podolsky, and Rosen, written in Princeton. You have to imagine the time scale. Einstein had left Europe in 1933 after Hitler came to power. He actually hadn't been in Germany at that time. He was in Belgium and left for the United States. And he was in 1935, he was in Princeton Institute of Advanced Studies. And the story goes that he didn't know enough about English and about publishing in the American academia. So he got support by his two young friends, Podolsky and Rosen, to work on this. Rosen actually became one of the fathers of theoretical physics in Israel. And I want to make this remark now. I want to extend your statement about China also to Israel. I think we should collaborate with our friends in Israel and support them in every possible way. This is really my conviction. Okay? So, but coming back to this, so they wrote this paper which has not a physics name. The name is philosophy. Can quantum mechanical description of physical reality be considered complete? What kind of question is this? You know? And what Einstein had actually observed, and it turns out that Schrödinger had observed this earlier. Schrödinger had observed this already in 1927, but he hadn't written about it, the Austrian Nobel Prize winner. And the point is, the point is if you have two systems which interact, so you can consider these two particles or billiard balls or whatever you name it, they interacted here, this is this low system here, interact here and fly apart. And then according to quantum mechanics, these two don't share their independent existence anymore. So in quantum mechanics we say they only have a joint state. If you do a measurement on this one, that instantly, without any time delay, whatever, changes the quantum state of the other one. Now, the question, this is something to think about. In addition, an additional fact is, here the citations of the Einstein-Podolsky-Rosen paper, which is quite interesting. The paper came out in 1935. It had only 5 citations. They were not bad. Two citations were by Schrödinger, one by Niels Bohr. So Nobel Prize winners quoting the work is not so bad, right? And then the field went completely silent. The field went completely silent because this question was considered to be just philosophical and not amenable to any experimental observation. Then in the 60s, an Irish physicist, John Bell, came around, and he said, wait a minute, if you assume somehow, that the measurement results here are given in some way by the properties which the system has here, but completely independent of what happens over there. Then you can show that some of the correlations predicted by quantum mechanics are stronger than your picture. And that suddenly made a philosophical question observable by experiments, and that's actually the experimental sequence is actually the story of our last, our Nobel Prize in 1922. Here are the citations. John Bell comes around right here, and then it goes up, and here the citations explode. And that is because entanglement suddenly became important for quantum computation, quantum information procedures. This was a completely surprise. You know, when we met all these friends for the first time in 1976, we basically agreed that this is absolutely useless. It's just philosophical curiosity. It can never be used for anything. Okay? That's the way it is. Now, this is old. It ended in 2012. Now the citations are at about 600 per day, which means that it's quoted twice a day. It's by far the most popular work by Einstein. But it doesn't mean that the paper is read twice a day. That's a different story, you know? Now, I want to come to some experimental results. This picture you already have seen by Serge Roche. I should say that in the late 1980s, I will tell you a little more. I decided with my friends to work on quantum entanglement. Before, I had been working on neutrons only. And with neutrons, it's impossible to observe entanglement in the laboratory because the density of neutrons in a nuclear reactor is much too low. You can completely forget that. The brightness of a nuclear reactor in terms of particles is the same as that of a very, very low intensity flash bulb, you know. So it's nothing, you know. Okay, so we decided to work with photons. And here's a picture of the source we developed in 95 in my lab. And one point I like to emphasize, and particularly like to emphasize when politicians are in the room. When we started these experiments in the 1980s, late 1980s, we had no idea how to achieve our goals. We only knew that this is extremely interesting if we want to do that. We did not know how to really detect the photons on an individual photon basis. We did not know yet how to make the states nicely. We did not know yet how to handle them and all this. And it took us 10 years to realize these things. And the point I'm emphasizing this now is in modern grant applications, and now Professor Kalako should also help in the future. In modern grant applications, you have to give a roadmap. You have to say what you want to achieve when. You have to say with what means you want to achieve it. You want to say what goal you want to achieve and so on. This is all not very good for creative science. Okay? One has to have a trust in people and give them support for doing fancy, curatorial things. Sometimes you might be wrong. Sometimes it doesn't work. But sometimes you get the golden nugget. Now here's an application of this. So we produce our pairs of entangled photons. Actually, I should not skip this because you don't. Here we go. Because I want to translate. These are the two cones which you saw already before, coming out of a crystal. Non-linear crystal pumped by laser. And there are two cones, there are photons coming out, and they are pairwise, you know, one comes here, one comes here, one comes here, one comes here, and so on. And they are polarized along the cones, but the cones intersect. And on the intersections, the photons do not know what their polarization is, either this or that. Completely undefined. They have no well-defined state, completely undefined. The result is completely random. But what is defined is that this one has to be orthogonal to this one. And that's exactly the nature of entanglement I told you before. Individual results random, but perfect correlations. Here's the application with quantum cryptography. We just use such an entangled source. This is a historic paper a while ago. With an entangled source, send one photons along a glass fiber over there, one over a glass fiber over there, over, at that time, over a distance of 300 meters, measure their polarizations, and we get a random sequence here, and we get a random sequence here. But because of entanglement, the two random sequences are identical. Now, if you have, every cryptographer knows if you have a random sequence, you can use it to secretly encode any message if you use it only once. But you need the same random sequence to decode it. In quantum cryptography, in this kind of quantum cryptography, the other kinds, the point is you do not have to send the secret information, the code, from one place to the same, because it comes into existence spontaneously at the two locations. So there is no spy who can catch the information, nothing. Just like that. Now, I want to mention here the results at that time. What you see here is, here are the two keys, the random sequences, at one side called Alice, Bob at the other side. This is just an optical representation with an 8-bit deep color code. But it looks pretty random. But you can tell that the two are the same. For example, by just looking here. Here we go. Here is this dark spot here. Here's the same kind of dark spots. Okay? And so what happens is that you mix bit by bit this with the original. That's a digital map of the famous Venus von Willendorf, the famous figure found in Vienna, 25,000 years old. And actually, this is probably the most famous Austrian lady. Because whenever I give talks, even in Australia or whatever, they know that. They see that in the school. And I tell you why we choose it. When my students came to me, and they had a bomber, picture of a stealth bomber. They wanted to encode that. And I told them we need something which has two features. Firstly, it is Austrian. And secondly, it is beyond any doubt no military symbol. Okay, so this. And the rest of the story is simple. You can imagine that. Now here's the encrypted picture. Actually, the mixture of the original with the code. We send this over. Since this is random, and there's no structure. Since this is random, this is random. There's no structure in it. And Bob can decode it and get the original. Now, this field has really exploded now. There's lots of activity all over the world in various forms of quantum cryptography and so on. And I know many of you know more about that than I do. Now comes, how much time do I have? Professor? 8 minutes? Very good. So I have to cut my slides. Anyway, so this was actually the starting point for me. In 1987, three of us, Greenberger, Horn, and myself, found out that if you have entanglement not between two, but between three particles, in that case, three photons, you can have correlations between the three, which are even more counterintuitive than with two particles. In the sense that for each individual particle, if you have quantum physics makes a prediction opposite to that of classical physics. And we wanted to do that, and that was my goal over 10 years to achieve this kind of thing, which we finally did in 2010. Here's my friend Mike Horn, who passed away unfortunately 5 years ago. I dedicated my Nobel speech to his memory and to the memory of Helmut Rauch. Here's another application. This was a collaboration with China, intercontinental quantum key distribution between China and Austria in 2018. That's actually a European story too. I tried from about 2005, 2006, one should look closer, to get the European satellite activity going. I was not successful. That's probably my personality. I don't know. I did not succeed. I simply did not know how to get this going. With all these rules, you have to have large member countries and people from smaller member countries and so on. It didn't succeed. And then one day, my student, Jian Wei-Pan from China, calls me and says, "We are launching a quantum satellite. Do you want to collaborate?" He was my student. He's now a big operator. There are about 300 people in my academic tree in China, which follow from him. He was my student. And I said, I had one question. My first question was, how much money do you have? And that's also maybe something interesting. He said, $100 million, but that is just a line in the budget. Okay? I don't know whether Europe is able to make such decisions. The second point is, I told them immediately that we collaborate under two conditions. No single penny crosses the boundary, so there's no money coming from China to us and nothing from us to China, and no scientific information crosses the boundary. So we build our devices completely independent, and you build your devices completely independent. The Chinese built a satellite on their own. We just built the ground station. We only had to make sure that the two were able to talk to each other, because otherwise it would be useless. So we had this Chinese satellite, which is still up there, which made communication with China, made communication with Austria, and that way we were able to transmit the information. Now, these were some small cases of applications. We have something for the discussion. 5 minutes? Okay, very good. Thank you. Now, I told you back to curiosity. After having done these experiments with two-state systems, we worried what happens in high-dimensional entanglement. Suppose you had two pairs of dice, quantum dice, which are entangled. Now you cannot. This is just. Oh, the steering thing fell down here. Oh, that's amazing. Here it is. Here it is, right? The two quantum dice, which are entangled, which don't exist yet. But I'm sure in 100 years you can put it under a Christmas tree. That's another question. Okay. So if you had quantum dice, the result could be not just with polarization up or down, or spin up or down, or whatever. It can be 1, 2, 3, 4, 5, and 6. And you can imagine a quantum state which is such that it's entangled. It's entangled in this way. 1, 1, so you know, plus 2, 2, plus 3, 3, plus 4, 4, plus 5, 5, plus 6, 6. Now that means that you can install so much more information into just two systems than before, and with 6 different options. Turns out that in cryptography, such high-dimensional systems can be made more secure, but besides that, it's fun to think about these things. Okay, this is more the abstract description. And then we started to worry about how to build experiments for higher dimensional systems. Because again, this was a completely new field, at least for photons. And it was difficult. We knew we want to create this complicated state like this or other ones. And we were sitting and trying to make drawings, and it did not work. We did not get a good result. And then one of my students had the idea, and he said, well, why don't we write a computer program for that? Okay, so we wrote a computer program. We called it Melvin. Melvin is not an acronym. Melvin is just the name of the computer. computer program, okay? And what this program initially did was it had a toolbox, built up some systems, and then we checked whether it was the right thing or not. And in the time we learned how the computer program can learn what we are doing. And in hindsight, this was probably the first artificial intelligence system building quantum computing solutions. And the computer found solutions which a human would never have found, I claim. Not because it's so complicated, because it runs so much against human intuition. Okay? I'm coming to my, here's an experimental realization found by Melvin for a three-state system, experimental realization found by Melvin for teleportation of Q-treats and so on. And no, 1 minute or two. You should never, you should never believe this, Chairman, Right.
But you see, Anton, I would really like that we have.
But I agree. I'm finished in 2 minutes.
Okay.
I'm finished in 2 minutes. Another fancy application, which has not, which we found a couple of years ago, but which really has not found complete applications, is that you can actually use entanglement to make an image with have two photons, one at high energy, one at low energy, and suppose you want to study some biological samples at low energy, but you only have good camera at high energy. Then you can have it such that the only low energy photon sees the sample, but the picture is taken by the high energy one, which has never interacted with the sample. This is actually very curious. And it's slowly keeping up now. How fast can I push the forward button now? This is all not so important. This is one of the most last examples how we can create novel entangled states in a fundamental way. Here's a picture where we actually started. No, this is not important. That's actually a short picture I want to explain you. We did a test of Bayes inequality with two photons. It's better. Photon pairs created here and sent to two telescopes here, but only to the bases. Here we measure their polarization, and then up there we had telescopes which looked up to quasars billions of years ago. And we used the light of the quasars as independent decisions of what is being measured, because we wanted to make sure that no common influence is influencing this. Now, this was fun, and we are continuing with gravitational waves, with neutrinos and so on. We're actually studying this. We are crazy enough. And I want to finish with this one statement. Einstein, after the 50 years of conscious brooding, all the 50 years of conscious brooding have brought me no closer to answer the question, what are light quanta? Of course, today every rascal, in German Hinz and Kunz, thinks he knows the answer, but he is deluding himself. Thank you very much for your attention.
So thank you very much, Anton. So the organizer just agreed that we have now a mini roundtable with 3 speakers to maybe 15 minutes. Ignacio and Serge, you may sit also. Just to answer the question relative to the talks. There will be another more general roundtable now, but I think these 3 talks were quite interesting and stimulating. So I hope you all took notes and that you have questions related to the talks. So somebody is moving with a mic, maybe. So I don't see very well, but.
Nobody. Everything was clear. Chairman has to ask.
maybe with Ignacio. So yes, there is this question of quantum advantage, NISQ, not NISQ, fault tolerant, not fault tolerant. So it's a very delicate but very actual problem. So do you have some?
I mean, quantum advantage has been demonstrated, but that's not a definite answer in the sense that when this in 2019, I mean, Google had this quantum advantage experiment. Then at that time, with a classical computer, it took, let's say, 1,000 years to solve the same problem. However, in the meantime, classical computer found new algorithms, new methods, and then at some point they beat it, even the quantum computer. And then people building quantum computers enlarged a little bit the systems and beat the classical computers. And this also touches on some point that I wanted to remark at the end of my talk, but I didn't have time, is that quantum computers and quantum simulation is not only, or they are not only useful just to solve particular problems, but they are teaching us. And in the field of quantum simulation, we are learning with quantum simulators new methods, new physics, and in particular, even new classical methods to describe many-body systems. So I don't think that the goal of quantum simulation is just a black box machine in which you put a problem and you get an answer, but rather is something that lets you to understand it better and then develop many other things around them.
I like very much this answer, Ignacio, but I would say it's a physicist answer. So I don't know. You see what I mean? That's,
no, I don't know what you mean.
Never mind. So are there other questions? Follow-up, maybe lady here.
Thank you very much, and thank you for your very nice talks. So this question is from Professor Zeilinger. So do you see, so basically all quantum computers that nowadays people are designing are two-dimensional, although we start seeing some examples of high-dimensional quantum computers. So do you think that there could be an advantage to do computation in high-dimensional, with high-dimensional systems in the future, or do you envision some interesting experiments with that?
Well, so far, I can only say that there's an advantage in quantum cryptography in sending information, because high-dimensional systems can be more secure than just qubits. Okay, I cannot answer your question concerning quantum computers. I think nobody knows that answer. There are reasons that scaling into higher dimensions does not scale as well as taking more qubits, but these are abstract reasons, so I don't know what's going to happen. On the fundamental issue, they're very important question in higher dimensions, and it concerns the orthogonality of states. I know two states are orthogonal if one doesn't tell you anything about the other. And in higher dimensions, it's a really open question how many sets of orthogonal states exist, namely independent ways of encoding information. And that's quite interesting. It's a question which is attacked already for 20, 30 years, and we have no good answer. So my heart is at the foundation, so that's the reason I'm interested in that.
Thank you. Other questions? Yes, here a question.
Quantum computers are well, the quantum computers we have now are noisy and probably will be noisy for some time, maybe forever. You have not mentioned error correction and the role that this may play in making quantum calculations useful.
Serge, or you want to say something?
I tried to mention it when I talked about the bosonic correction code. The fact that the big problem is that they involve a lot of overhead. You have to code a logic qubit to a very large number of physical qubits. And for example, in the case of superconductors, if you consider the number of physical qubit to make a logical qubit, it's a rather large volume. So your computer, to be useful, would be cubic meters in size at very low temperature. It looks like the computers were in the 1940s. And we don't know how to make it smaller. And So the question is not whether it's theoretically possible, but the question is whether it would be ever practically possible. But I think the question is open today. May I add one remark about what Anton quoted Einstein in the quotation of Einstein paper? I think we can learn a lot of interesting things about that. First of all, I think it's rather strange that the other paper by Einstein are quoted much less than this one. This reminded me of an experience that we all might have had recently. I received an email from a company which is ranking the scientists of the 20th century according to their citation index. I looked at this list, and the first 10 I'd never heard about them. So then I wanted to find out where Einstein was on the list. Einstein was listed at the 765th most influential scientist. Then I tried to look at my position. I found myself at 1,600th place, which I think is very nice. It means that I'm only one half of Einstein. So I think this joke, all joke aside, joking, I think there's a lot about the importance of citation and that you should take them not only when they concern Einstein, but when they concern anyone with a grain of salt, and be careful about judging people according to citations.
Well. Yes, other questions? Yes, okay.
Thank you for the inspiring talks. And my question is in particular for Professor Zeilinger, and this is about quantum entanglement, and in particular the classification for entanglement that for entanglement between more than 2 qubits and more than 3 also. So I know that nowadays the type of classification that we have, it's not so satisfying, and so I know that there are some studies on trying to use machine learning techniques in order to classify them. And as an example, that the work that your group did that tried to, that achieved some insights about new ways of entanglement, do you think that it could be possible to use machine learning to try to deduce new criteria of entanglement? Because maybe the criteria that we have up to 3 qubits are not so satisfying when the number of qubits grows. What is your thought about what machine learning can do in helping us to deduce new criteria and not only to use the criteria we have and applying them?
Okay, thank you. I mean, it's also actually quite a while ago that I was working on the kind of how to classify entangled states, so I'm not a specialist anymore. But here in the room is Marek Żukowski, for example, from Gdansk, who really worked much more and knows more to say about it. What machine learning will tell us, I have no idea. I mean, machine learning, and you mean artificial intelligence. If it's artificial intelligence, I understand for the best results you don't even want to tell the machine what the machine should look for, right? But I don't know, I'm not a specialist for that. I mean, in our case, it was a big surprise. And in our case, I can only say, we wanted certain states which we considered interesting to be realized. And we started to make drawings which somehow reflect our intuition of the symmetry and features like that, which are contained in some definitions of entanglement. And then the computer didn't at all care about that, and the computer gave solutions with much fewer elements, which scaled much less than our things, and which completely ignored any symmetry considerations. And the results were in part so complicated that when you sit down and when you follow your finger through, then you convince yourself, yes, this is a solution. But the next morning you forgot it again. Because this is, human intuition does not work that way. This is this is an appeal to human intuition, actually, what I just said.
Thank you. More questions? Yeah, I have a question to Serge. You spoke about the two things. In my view, the very first quantum gates, Sirac-Zoller code, were very much inspired by high-resolution spectroscopy, atomic clocks, Ramsey fringes, all these ideas. So it was atomic physics, basically. And then it moved strongly to solid state, superconducting qubits, etc. Now there is sort of a return to atoms with these Rydberg interactions. So can we get a lesson from that?
I think that what is fun about science is that things are evolving in time and you don't know where you are going. I think what is also what I find very positive is the fact that you have competition. I remember when we did our experiment in cavity QED, it was a time when the superconducting qubits were starting. And there was a strong competition, and we're happy about that. It meant that other people were interested in what we were doing. And I think now atomic physics and cold atoms are coming back at the front. Maybe some superconducting people are worried about that, but I think they should not be. It just means that there is a lot of positive competition, yes, and that we learn from each other. And what I found very interesting in all these fields, which developed over the years, is the fact that it put atomic physics and condensed matter physics much closer. And one field is very fruitful for development in the other, and I think it's very positive.
Yes, there are recent rumors that there are experiments by Michal Lukin in Harvard, which makes Google very worried.
Yeah, but I think this is a little bit childish to think in these terms, and there is a lot of public relation in all these fields. I won't enter into that.
Yes. Anton, you wanted?
I have a question, actually, and that concerns what kind of complexity we quantum physicists assign to classical problems. Mm-hmm. This is all theoretically very nice. You showed us that and so on. But I learned, for example, about the traveling salesman problem. I learned from someone who really works on that. He said that all these arguments are not valid for us. Mm-hmm. He said for any traveling salesman problem of any reasonable size, we have programs which can solve the problems in fractions of a second. So this is not a good argument. I wonder how this is interpreted by us, yeah, or whether it's the opinion of the other community, so to speak. Right?
Yeah, I mean, but this is connected to your first question about the quantum advantage. Mm-hmm. And so this traveling salesman is an optimization problem. And what one can show is that it's very hard to find the optimal solution. So what people will tell you classically is that they can find a pretty good one.
A good enough solution for any practical purpose.
Good enough. So now the question for quantum advantage is whether a quantum computer can find a pretty good one or even a better one in a shorter time. Mm-hmm. That's the question of quantum advantage. Yeah. And now related to this advantage, it turns out that with noisy quantum computers, it will be extremely hard. Mm-hmm. And the reason is because with a quantum computer that is not perfect, that is noisy, it will never find even a pretty good one. Okay. And if you let the classical methods to have the same errors as you have with, let's say, noisy quantum computers, then they will have advantage. That's why some people have been trying these optimization problems with these devices, and at the moment, unless these devices are much better, have less errors, will not have a chance to improve them.
Thank you. So there is a question down there at the bottom of the room. And yes, we have already almost finished.
Thanks a lot for this impressive talks. My question is related. We are talking about entanglement of photons, but I'm worried about, because I come from the condensed matter point of view. So the question of topology, the question of the protected states, could be contribute positively to the question of the entanglement of the protection states. So my question is, could topological quantum entanglement contribute to the development of modern and different technology in the future?
May I answer that? Yes. So maybe people don't know what is this topological things. And okay, so in the end of the 90s, there was a a very famous paper by some scientists from, now it's in Caltech, who proposed a new way of doing quantum computation which was very resistant with respect to errors. It's called topological quantum computation, and it's related to some properties, exotic properties that some materials would have. These materials don't exist, but if we would create them artificially, then they would be more resistant against decoherence. And this would be good for quantum computation, for example, because we know that the main problem in quantum computation is decoherence. Now, that's a good point. However, to create these materials that artificially actually is very difficult and gives errors themselves, which so far cannot be corrected by the system themselves. So these are not robust. Still, there are people working on that, and so it may happen that in the long future, now we didn't have them in our, when we talk about the different platforms in which people are trying quantum computers, we didn't include this topological quantum computation because actually they are not very far, they don't have even a single qubit. But maybe after, if they have a good development, then they will be able to use that, and then it would be a competitor. So the answer is not at the moment, maybe in the far future.
Thank you, Ignacio. So I'm sure there are more questions. I have more questions, but the time is more or less out, and we will have one more roundtable after the break. So now it's time to have a coffee. So let's thank the speaker again.
Okay. We still have another roundtable.
And therefore, can you hear me? Yes. Oh, wonderful. Oh, now it's working. I think that the technicians heard me. So welcome back. We are only 35 minutes late. And so I have been told that I should either cut it by 35 minutes or maybe not. So that's kind of a free format. But I am told that we should be finished by 7 p.m. maximum. Okay? Otherwise, there is no telling what will happen. So, so the way so we heard already a lot of statements about quantum in Europe, about science policy and so on. So the first thing I am going to do is I am not going to allow any introductory statement, because we already had plenty of those. Oh, you want to do an introductory statement?
The sound is very bad.
There is a lot of echo.
A lot of echo.
There's a lot of echo.
There's a lot of echo. What can I do?
Bad for physics.
I can stop talking. I can talk without mic. Lot of echo? Still? They can hear. They cannot. You cannot hear me. That's bad.
I have a mic here, and I think it works.
Oh,
right?
okay. Should I take that?
Sorry? I'm fine with that.
You're fine with that. Okay.
I'm happy.
Okay, good.
That's
so
fine.
I don't know what to do, because I'm not in charge of the technical aspect. Anyway, what I was going to say was that I am not going to allow any introductory statement, because we had a lot of those before. And also, I'd like to, okay, you can have this sort of policy roundtable in a very scripted way, in which you tell in advance everybody what you're going to ask and so on and so forth. I didn't tell any of the participants here what I was going to ask. And I am going to ask the same question to everybody here, because I would really like to have some really panel discussion. So it would be good also to have sort of an exchange of opinions from different points of view. Because as you can see now from the slide, which fortunately has been switched on, we have here not only science, which we have already seen, but we also, and policy, which we have already seen, but we also have, of course, QuantERA, which is in between science and policy. So this is Professor Elisabeth Jacobino from the French National Research Agency, who is a high-level representative of QuantERA. And then we also have industry, which is Enrique Lizaso, the treasurer, and a member of the leadership team of the European Quantum Industry Consortium. So we also have industry. And so what I'm going to do is, as I said, I will ask questions which are inspired by what we heard before. So we heard, for instance, one thing which I liked very much from the talk by Thomas Cordas was the sort of SWOT analysis that he gave. Not only SWOT analysis, but clearly also to-do list, which I think was very helpful, and I know that several colleagues appreciated that. Also, I heard some questions which Serge asked at the end of his presentation. So I'm going to ask them to all of our panelists, and I will do that in a sort of focusing on feelings. So each of my questions will refer to a feeling, and it is a personal question to each one of you. And of course, the answers have a lot of sort of import onto strategy. So my first question about the first feeling that I want to explore with you is, this is a session about quantum in Europe. So what does each one of you like most about quantum in Europe? Kike.
Thank you very much. Tricky question as it is. Well, the easy part is for sure talent. I mean, Nobel Prize is here. I mean, this is just a demonstration, and then a particular nice place just to get the talent that you need for, in this case, from the industry. I came in representation of the European Quantum Industry Consortium. So this is something that which is really interesting. So if you want just to build something based on serious science, this is the place, obviously. Okay, this is what I really do like. I also like well, it's the sense that, at least in this field, particularly in quantum and in quantum computing, that is the one that I came from, it's also something you feel that Europe is moving differently from some other fields, in the sense that we appreciate the urgency in some cases, and also the need to do something just to make this, as an industry, a strong part of the new Europe that we are building. Those are the very good things.
Okay. Ignacio, what do you like about quantum in Europe?
Well, I think that what I like most is, or one of the things that I like most is the history that we have together in quantum science. So if, I mean, some of us have been working already for many years in this topic, and it has been always a very cooperative and friendly environment. So we had always a lot of support from our governments. We have support from scientists. We have support from many people. And this has been, I think, like a club, and we have been exchanging results in a very, I think that we've mentioned in the coffee break, positive, constructive, competitive environment. And as compared to some other fields or some other areas, I think that makes it very singular.
Okay, thank you. Well, we see, I mean, this is a question which typically is telling us where each of us is coming from. Maybe since there is now a mic, which I don't know, there is plenty of mics, so maybe plenty of echo. But Thomas, now you have the mic in your hand. What do you like most about quantum in Europe?
What I see in front of me, this is what I like. That is a whole dynamic community, you know, that you have the impression that it's like a baby. Actually, it's not a baby, because when we see what's going around, we have plenty of scientific wisdom all around, but at the same time, it's a kind of newborn community. And this is what I like, is that the feeling that things are changing, even if they are changing little by little, even in Europe, where sometimes we are a little bit too much, you know, blocked in some of the thinkings that we have and some of the usual weaknesses that we show. But really here, I see things evolving in the right way with an ecosystem that is emerging and that is taking shape, and which shows that we can do it, but we need to be extremely careful when this baby is growing up on the way to do it, and how to do it, and how to make sure that we do the right things and not all the wrong things that we did in many other areas.
So now, of course, I'm not supposed to say something that I like, but I really have to say this because we have not scripted this. But when I asked a similar question to Gustav Kalbe, the director of whom Thomas is the boss in the European Commission, at our conference in Hanover a few weeks ago, I got the same keyword, and this is really amazing. So they both spoke about community. I think it is actually quite amazing that the funding agency, you ask them, the first thing they speak about community. I mean, I really wish this would happen in many more member states, yes, of this continent. So, oh yes, Elizabeth, you want to say something?
Yes, I wanted to, but...
I don't know, yeah, okay. No clue.
No, it's absolutely great to be here and to have this European community present. And I must say, it's fascinating to see how this quantum European community has grown since when I started, you know, in the 80s and 90s, we were living on European projects with some networks, smaller than here, of course, but it was fantastic to build this network. We became friends. I mean, we had all these friends all over Europe working on these quantum projects, and it increased, and with ERANETS and with QuantERA, it became fantastic. You know, we in this QuantERA, we have almost all European countries, 41 RFOs, which are holding that. And
RFOs means research funding organizations?
Yeah, the research funding organizations, sorry. And all the people from these funding organizations have been working a lot, meeting regularly to build this community. And this was held by the NCN, the Polish national organization, and Sylvia, who is there, was really began with this fantastic story. And not only all the RFOs really succeeded in setting this organization together, and together, of course, with the European Commission, but also, you know, there is a presence of a lot of this, what we call widening countries, basically the former Eastern countries anyway, who usually didn't participate so much in these European actions. And although people are very good there in mathematics and physics in particular, and we were very happy to have this very broad community building in this system. And of course, this was also supported by the quantum flagship, where we have the founder here. And all this is absolutely unique, I think, for this research organization in Europe. So.
Oh, thank you. I saw Serge nodding. Yes, so maybe you want. One really should say last but not least, Serge and Anton.
No, I agree with all I've said. I think it's very important to have a community working in this area because we need a critical mass in Europe. We are facing other countries which put a huge amount of money in research in quantum IDs, but also other fields of research like China and United States, and each country in Europe is not able to do the same. So we need really to cooperate and collaborate. I have seen on this poster that this sentence, quantum IDs are born in Europe, but you can extend that to other things. It's not only quantum IDs. I think you can say that physics and chemistry were born in Europe, and so we need really to go on and to be able to pursue good basic science at the European level with European values, and I think it's very important to have this at a level where many opportunities are given to people from different countries in Europe to work together, to exchange ideas, and to collaborate together with the rest of the world is also very important. I am very much concerned by the fact that there are now geopolitical tensions which make science, to work in science, difficult across boundaries. There is a lot of difficulties to collaborate between the United States and China, for instance, and I think that in spite of the fact that ideologies are very different, that the political views are very different, it's very important to keep open all the channels and not to stop working together under the pretense that we are working on strategic issues which will force us to be to respect classification of research, for instance. I think it's very bad and dangerous, and we should avoid that, especially even in the work of quantum computing. I think we are at a stage where it's still basic science. We are not at the level of a Manhattan Project, which would give a strategic advantage to one part of the world above the other. And I think that we have to avoid this spirit and to keep the collaboration open as much as possible, to the point where we respect the same values. And I think it's still the case between United States, Europe, and China. And I think we should go on and not have boundaries.
Thank you so much. Well, actually, one thing I like about this, of course, everybody can also comment on what anybody else has said. One thing I like is that maybe opinions can emerge which might have differences, you know, so the points of view. Oh, you already have.
I don't need you. I have my own microphone. I'm autonomous, as you might know, for some time already.
I kind of guessed.
Right.
Go ahead.
No, at first, now a question to the technique acoustic up there. There's a microphone. There's a speaker up there which sometimes works and sometimes does not work. Hello, can you hear me in the room? Maybe they only speak Spanish. I don't know. This is really a problem with the acoustics. This room is designed for broader acoustics, but this one doesn't work. Well, maybe we can forget that. Okay, I know too much about acoustics because I had to worry a lot in other institutions. Anyway, so what do I like about quantum in Europe? In Europe, I am convinced, we have a unique intellectual tradition. And that tradition in Europe is basically concerned that it starts at least with the Renaissance, that we have learned to talk to each other and then even to collaborate in situations where there could be political problems, where we might disagree, etc., etc. This is unique, and we also have learned in Europe to an extent which I think is very special, to handle extremely complicated solutions. This is a European specialty, I think. I can talk about other continents too, the way I view them, but that's a different story. But we have a unique tradition. And this is something which, in my eyes, is and should even more be preserved on the European Commission level, without giving up a coherent thing. When we come to quantum, as it has been said, some of the most fundamental contributions over the history came and are still coming from Europe. There was a change during and after the World War II, partly or mostly because of immigration from Europe. But we have recovered from that. We have recovered from that in the 1970s, roughly. And that is a very important thing, that we foster very strongly fundamental questions. Because number one, this is extremely interesting. You know, in the same way as people probably for at least 50,000 years have been looking up on the sky and they're wondering what is going on here, what is this? And that's a completely useless question until very recently, until the GPS was invented and things like that. You know, and this is part of humans, and there are some among us who are curious and who just want to know what's around the next corner, even if it's dangerous. And some of us say, no, let's stay put, I don't want to move. And both of them are important. And in Europe, I think we have much of that. In America too. In America, they have the frontier thinking. No, just go to the next frontier and so on. But we know the Americans have run out of frontiers. The next frontier is Mars. I understand. That's the story. So I think we should also within these networks, we should more consciously support fundamental research, even if it cannot tell you what it might be useful, etc., what it might be good for. So we have to have mechanisms. We also have to have. I understand if you want to have a product in industry, you need a roadmap, you need a time scale when this is developed, etc. That's the extreme case, but not always. Not always. There should be a broader spectrum of how to talk. You know, when we started the first quantum discussions in the Pathfinder project in the 1990s, I was already worried about roadmaps, etc. And I was told that this is just a way how you can talk to the Commission. Maybe we overdid it a little bit. Maybe there should be a little less, there should be more openness and so on. And I would say I want to make one more provocative statement, which was not the last one. That one more, if somebody writes a proposal and after 3 or 5 years, he or she still follows the original proposals and is proud that the original goals were met, then it was probably a waste of money. Thank you.
So, well, it's good that we did not have only, sort of good feelings for this first easy question, but also some, maybe provocative statement, as you said. That's very important, sort of, to look critically at the future. And of course, certainly there can be many different points of view. One thing that concerning this, 20 years ago, we called these roadmaps. And then we stopped very soon calling these roadmaps because a roadmap is exactly what you said, where you say, okay, now I know the step and this and that. And actually, the way we started calling it pretty soon was more like a research agenda. And actually, again, what was underscored by Thomas before and also by Gustav Kalbe in our discussion in Hanover, is that this is taken as a reference point by the Commission and maybe in the future also other funding agencies, in the sense that it's not so much we predict, we promise, it's in the sense of what's the vision, where we want to go, how much we know, how much we don't know, so with a certain openness. So it's much more open than this kind of roadmap for semiconductors, so to say, in which they say, okay, now we go to 5 nanometers, 2 nanometers, and so on and so forth. So I think that there are elements of that. But at the same time, I would like to go for a sort of more difficult question, okay? So after some good feelings, let's say, one about perhaps not so good feelings. So I would like to hear, then we will go back to good feelings, don't worry. But for the moment, I would like to hear from everyone, what do you miss most concerning quantum in Europe? And since this, everybody is invited to think about this, of course, and to also give your point of view, maybe afterwards. And some brave person now is ready to give us an answer. What do you miss most, Elizabeth?
No, it's a very easy question, but everybody suffers about that. It's all these calls for, proposals and so on, and a very low success rate. Okay, and so that means that everybody writes proposals several times before they are accepted, or sometimes they are not accepted, and this is kind of ridiculous because even if you see that from the statistical point of view, it doesn't work. We know that when the success rate is very low, it's like a lotto, and it's just a discussion between the people who are in the panel that count anyway. So this problem has been, by the way, solved in Switzerland, but now there are less and less in Europe, but because at the Swiss National Fund, the success rate is close to 50%, so much better. So this is one of the main problems because people waste a lot of time with this proposal writing. Of course, they also learn things, and for example, in France, we are not too good to say fantastic things about ourselves, so this is something we learn from the others. Anyway, it is one of the main problems of research now in Europe.
So this is certainly...
Not only in Europe, but also at the level of national calls.
Yeah, this is certainly a point of view which probably also other scientists share. One thing that one could remark is that sort of success rate of FET before the flagship started was a subshot noise. The flagship has really improved that a lot. So, it used to be a random process in the end, but now, it's kind of, it's simply significantly higher. It's not 50%. I would say that the success rate in our field is certainly regarded to be definitely higher than in other fields, and maybe other fields are jealous when they look upon us because of this. But okay, so this is one example of a controversial thing, but it's a scientist's point of view. Do we have other points of view from either science or policy or industry about what each of you misses most? Ignacio. Excellent.
Yes. So what I noticed is that the level of bureaucracy has been increasing at the national level and then the international level. So I don't know how it's in other countries, but now when you want to apply for a project, want to report for a project, then it has to do a lot of bureaucracy, and this makes everything much less expensive. That's nothing that I'm just inventing myself. That's something that we have experiencing in every day. And this, I don't know, I understand that, of course, one has to be very careful with the public money, with the money from the EU, but on the other hand, this has to be more efficient and more competitive. And I think that that's a problem that we face, that at least the people who are surrounding me have seen, and it would be good to have a solution for that.
So how is your experience in this sense comparing sort of the level of you know, complication at the EU versus national level?
Well, at the level of my institute, let's say you want to research, get some funding for research, there is basically no bureaucracy. At the level of the national level, it's, it's quite a lot, in fact, and depends on the money is coming from the ministry, it's coming from the Bavarian government, or it's coming from somewhere. But the EU level, it's higher. And so that's what has, that's happened in some of the projects that have been. That before we needed a coordinator, and we need 2 or 3 coordinators just to take care of the bureaucracy, and I think that that's something that we are suffering. And I don't know if this is there is a way around it, but I think that that's something that people have been concerned.
Okay, you grabbed the mic, Serge. Do you want to say something?
I think that the problems which you raised is especially important for young researchers. I think situation of young researchers who start their career makes life very difficult for them, because they have to compete for grants from the beginning, and they spend a lot of time writing grants, and they are submitted to this randomness of grants acceptance, which make the situation difficult for them. Another problem is the fact that there's now a competition between academic research and the startup research. So a lot of startups are hiring at the postdoc level, giving salaries to the postdoc much higher than the ones they can get when they work at universities. And this is a perverse effect of this passion about quantum science, the fact that it attracts a lot of bright people in applied science, and it makes it more difficult to get very good people in basic science, which is mostly what the academic world does. So maybe one should have a better collaboration between research in the academic and in the private companies, which make basic science shared more evenly between the two, and also make it possible to attract young, bright people into basic science. But for this, I think the institutions, maybe not at the European level, but the national level, should make efforts to get better positions for young scientists. And I think young scientists are more attracted by curiosity-driven research than by applications. And it does not mean that they will not get involved into applications later, but I think to attract people because they are interested in curiosity-driven research without any goals is very positive, because it will bring young scientists into research, and after that they might be interested into applying their research for practical purposes. But we have to make sure that we get a community in which we can get bright minds and give them a way to achieve their goals and to have a good career. And there are problems about that, the fact that there are less and less positions, that the positions young scientists are not paid well enough. There is a competition with the outside world, with other countries outside Europe, which provides much better living conditions. All this, I think we have to nurture basic science in this way to attract young people into this kind of research. And this is true for the quantum flagship, and it is particularly true because there is a lot of money going into this field, because it is promising for marketable applications. But one should not forget that it all starts with basic science. And
so still, in your one thing, absolutely. So you underscore that also in your talk today. One thing that I took note that you said, and I was pleasantly surprised, then we'll come to pleasant surprises afterwards, was that you mentioned that there are marketable products from startups and many other applications emerging, some of which are unpredictable, of course, which is the aspect of what Anton was saying, you cannot plan everything. But you seem to sort of to refer positively to also this side, which is sort of complementing. I don't know if maybe Enrique has some reaction from the side of industry, because I mean here the competition for talent with industry has been mentioned.
Well, can you hear me? Yeah. Yes. I mean, from the point of view of the industry, we tend to see or to have a view of the global thing a bit different. It's not only about science, where in Europe we are fantastic, we are great, and so on, but it's also about the future. What happens when the people, let's say, from academy, just decide to get out of the academy or just found their own company or so on? Trying, for example, just to go on making research, applying, but also competing with some other, let's say, countries or even continents. So, and this is where the things start to get messy. What happens here? I mean, we have a very good talent, but then you have to start competing with companies exactly the same as you, founded by the very same people as you, in some other countries where they have access to something which is now capital. We are talking about capital. We are not talking about grants. We are talking about just having private or public money in exchange of future returns, based on whatever future things or products you are going to develop with your quantum startup. And then the things here are quite different. Compared with the United States, which is the regular point just to compare, okay, we have the same, let's say, more or less amount of new startups. In fact, in QUIC, in the European quantum industry, half of the members are from startups founded by scientific teams, like a lot of people in this area. The point is, when you go and try to get funds, okay, it fails. In Europe, it's quite difficult to get a startup founded at the same level as the United States. And that makes a problem, a quite difficult problem, because if you don't have large companies here or the new companies here, you can think about, for example, what's happening in AI with OpenAI and those kind of things, then you are not going to be able to provide the positions for the people, also the scientists coming from the academia or so on. And you are not going to be able to cooperate in some cases with them. But even less, I mean, the talent is going to move from here to some other paths, which is good for the collaboration, that's fine, as long as you are not an European startup, because at that point you are transformed in something like, let me be a bit of ironic, the preferred provider of talent from some other countries in the companies. I'm not talking about cooperation in basic science, I'm not talking about that, it's completely fine. But this is something that we have to change. If not, we are not going to be able to develop a powerful industry, not only for the large companies, but also for the small companies, a powerful companies, and then the quantum will be exactly, in some other fields, a thing from the past and not the future. This is what we have to think about. I think that the Commission and some other European institutions are thinking deeply about that, in the sense that you have to provide the tools, the financial tools, not for free, but in exchange of something, just to try to develop a strong, a powerful European quantum industry. Not for the sake of being just European and just completely closed from the other countries, but for the sake that this is our house, this is our home. And we have just to deliver and we have to build up those industries. This is also, let me just, a few commercial sentences. I came from QUIC, and this is our reason to live. But this is a good thing. I mean, we have the opportunity just to rise this sector.
In fact, I was tempted to ask, because Thomas referred in his talk to specific things that he thought were missing and with actions, but I see that Anton even raised his hand, so I cannot resist.
I want to respond to what you said. It's actually it just came to my mind about 50 years ago, or maybe even more than 50 years ago. I was in Austria, the representative of the young researchers at the university. This was an elected position and so on. At that time, I realized that there was a problem in the mobility and in the mutual understanding between industry and university. And what I started was a program which was funded by the government, where young scientists were paid half a year or even a year salary to join some industry they were interested in, and this really worked. It started new careers, it started new collaborations, etc., etc. Now, what really worries me is that today, 50 years later, we worry about the same problem. So something very basic is not done correct in Europe. Something very basic. And this is not the fault of the European Commission and etc. It's something in our under thing. I mean, if you compare it to the US, everybody says it's easier to start companies in the US. But why don't we do something about that? What's going on here? You know, something is wrong here. You know, and when you talk about the European, I mean, I know that Google, for example, they reject any government money for the quantum computation project. In Europe, they hold their hands up. What's going on? Something is wrong here. I don't know what.
So I'm glad that you raised that, because even though, again, I'm not supposed to tell what I miss, but you know, I should say that what I miss, in this case, I would like to be a little bit self-critical in terms of the scientific community. I miss from the side of many of my colleagues a little bit of, I could say, entrepreneurial spirit, of you know, sort of openness to risk, to adventure, to you know, really you know, go beyond the sort of cozy borders of our labs. This is sort of perhaps a cultural feature which I miss, and which, in my feeling, contributes to the situation which Anton describes. So that's for me partially an answer to that for you know, a lot of our young people maybe. But that's just my feeling. But as I said, I wanted to go back to Thomas, who did address in the talk with some concrete propositions, you know, things that, in your opinion, are missing. So would you like to comment?
Yes. Look, my role is not to understand what, my role is to understand what is missing and to act, first of all. I will start with an anecdote. In my career as a very young, I would say, bureaucrat in the Commission. So in the 90s, we had a team of different Europeans going to Japan for establishing cooperation activity, not in quantum, but in another field. And at that moment, I was shocked by the fact that we were all in a big room, not like this, but rather restricted. And we had the industries and the scientists on the one way, the public authorities on the other side. And all of a sudden, in the middle of the meeting, I see some of our scientists shouting to each other. That is, the German against the French against the Italian against I don't know. And I was shocked, really shocked. So I asked the Japanese colleagues to go out of the room and let them shout. So that was 30 years ago. So a little bit maybe less than that. I must confess that a lot of things have changed, and I would agree with what Anton has said, that now the notion of more understanding that we have in each other in the scientific world, in the technological world, has fundamentally changed. And I see it on a daily business. And I'm glad it is like this, because now, thanks also to the European programs, we learned how to work together. We learned how to share programs together. We learned how to share bureaucracy together. But there is one thing we didn't learn yet. You need to learn really to our politicians that when you have a program of 95 billion, don't dilute it in 10,000 priorities. If quantum and another 5 areas are emerging, let's focus on those. What I'm missing really, Tommaso, is not basic research. I hear what our prominent Nobel laureates are saying. Thanks to them, 10 years ago, 15 years ago, thanks to their manifesto, we created the European Research Council. It is there, it's having good money, and it really serves. 7 years ago, because of the fact that we didn't want to have only basic science because we didn't have to have only roadmaps, etc., we created the European Innovation Council. It was just, a few years ago. Now, what I'm missing really is that, and I'm really not, I would say, proud about this, is that when I have let's say, 100 million euros, and I receive 10,000 proposals at European level, on the one side, you can say I can be proud because the calls are so successful. On the other side, you can be really sad because many of the people come to Europe because there is not enough national funds. Let's recognize that. Because you start from programs that are national programs. You need to excel in your country before you come to Europe to cooperate. So otherwise, it will not work. And the European funds are not, to spread around thinly in all areas, which happens right now. So convince your people. When we say that internally, nobody hears it. But you people can make things change. So that's why I'm insisting. If quantum is a priority, if AI is a priority, if the future virtual worlds are a priority, and 2, 3 other major domains, not to talk about, of course, the future energy program, the future biotechnologies program, etc. But these are our priorities for Europe. So convince your politicians that when we have 100 billion euros, that we don't take at the end $500 million per proposal, per area, because this will never work. It's not like this that we create, competitiveness. It's not like this that we make things change. And this is what I would really like to convey as message today. On the one side, yes, we do a lot of things. Many things have changed. We have a lot changed. And I do believe that a lot of our people are coming to Europe because there is a good environment, because our way of living and our fundamental values are totally different from any other part of the world, including in the States, including in China, including in Japan. But at the same time, make you hear yourself. So we have Nobel laureates here that can go out there and this time not only fight for basic research, but fight also for major priorities. Europe needs to be present because that's the only way we can change things. We cannot be excellent everywhere. We have to now choose where we want to go and how we go there. And I think this is the fundamental problem that we will have, and I will stop there. That one of the major problems that we have in Europe is now really competitiveness. In the last 10 years, we lost 10 points in terms of ICT markets. We were around 21, 22% in ICT markets from our industry. Today, 10 years after, we are at 11%. At the same time, the Americans went from 26% to 36%. So can this continue? You can say it's bureaucracy. You can say it's a lot of things. But one thing you cannot say is that there is a lack of culture in risk-taking, for sure. And second and most important, there is a lack of possibilities to focus where we are good and strong and reinforce it so that we can become more competitive and change things out there. Thank you.
Thanks a lot. This, I think, addresses a lot of things that have been said. I see some people nodding, so that's good. And well, okay, so now this was kind of the sort of one negative feeling round. But now I'd like a positive feeling round again, like about pleasant surprises. So if you think back the last 5 to 10 years maybe of quantum in Europe, what is it that surprised you personally in the best and strongest way? We are going in order of increasing difficulty of questions.
Let me start with a different point. Look, that was not 10 years ago. I'm not a physicist, I'm a mathematician. My co-founders don't let me just speak about quantum for the risk of making some erroneous statement or whatever. But look, in 2017, 4 people, 2 co-founders in my company, and which they are our physicists, we decided just to start some, let's say, startup. And we thought that that will be a quite a slow one. I mean, come on. Quantum computers are not fully developed. I mean, this is the real case, and it's going to take a while for that. So we decided, okay, let's start doing things, making speeches, and so on. Nowadays, the company has 100 people just working from there, and you attracting and more than half of the people came from abroad. And when I mean abroad, it's abroad of the European Union. So, I mean, this is surprising. I mean, even with the things that we already have here, I mean, here in the technical part, quantum computers and so on, you can still rise a lot of things and do a lot of things, 100 patents, etc., etc., etc. This is not something extraordinary. This is something that is also done in the United States. But I would have never thought, and none of my scientific founders thought, that what was even possible in the field, or even less, sorry to say that, at that time in Europe. I mean, now it's possible. So this is the kind of positive thing that you were asking for?
Pleasant surprise, yes. Now for more pleasant surprises. I have my own, but first...
Can I just say one?
Yes.
When you have your door knocking by the US asking you to cooperate, remember that. In quantum, by the way, and not only. You feel proud about what you have and what you have achieved. And you would feel even more prouder when the Americans start understanding that they cannot just come here and pick up our best minds and our best SMEs or startups, but they come here to also look for brilliant minds and brilliant ideas about what we can do together. But this has a price, and this is what we're saying right now to them. The price is that if we open our programs and our ways of doing, they should do the same. And the price is that if we, for example, ask them for getting access to some of the technologies they have, they should also accept the fact that they cannot just close down cooperation here and then come here also to ask just for scientific cooperations here and there. So yes, Europe, I think, can be proud about what we have. And believe me, it's not only the States now that are knocking at our door. It's also Japan, it's also Korea, it's also India and many other countries. Not so much China, actually. That's a different story we can maybe discuss a little bit later. But believe me that there are things that definitely we need to make sure that when we go out there, we have to be careful about what, not only about the fact that the others come to us, but what do we want to get from the others? What is the benefit for us to go and discuss with the Americans, not only about basic science, but also about technological developments, about what we can do together in the near and the longer term future, about, for example, export control elements also that are becoming more and more geostrategic, and many things like this. And here is where I must confess, we need a little bit also of support, also from our scientists. I mean, unfortunately or fortunately, the last 50 years, many things have changed. But one thing that changed in the last 5 years is all the geostrategic issues. And today, I hear a lot saying when we defined the horizon in Europe, everything was widely open for everybody, for the whole world. But this is a very naive way of seeing now things in Europe. And many of the communities, especially many of the basic research scientists, I make a sort of small parenthesis to say I understand why, of course, they're saying it. They believe that we can just continue this way. Unfortunately, not. And we have to be careful when we collaborate. We collaborate on what do we share, and how we share it, and what happens with who we collaborate. So nobody is naive anymore. So you know that things have become crispy in some areas, which are fundamental technologies of the future, where everybody is trying to get the best of the knowledge. And unfortunately, the world is turning around, whether we like it or not, and we need also to adapt our policies vis-à-vis that. When, for example, we were the first in the whole European Union, actually, to say we cannot collaborate on a number of areas because they need to be more protective here about what we're producing because we are at technological readiness levels that are closer to industry. And I hear 27 member states turning against us and saying, you cannot do that. This is forbidden. Why is it forbidden? I mean, so yes, we need to protect our industry investments. Yes, we need to protect the way the scientific knowledge is transferred from our basic research labs to the institutes, to the technological institutes, to the RTOs, and then to industry. This is what is at stake today. Unfortunately, things are changing and we need to adapt. Those days where we were 10, 15 years ago and we're saying we do everything together, by the way, this period was relatively short in history. It lasted maybe 10, 15, 20 years, is unfortunately changing right now. And believe me or not, we need your support and not just shooting at us when we decide for one reason or for another that we need to be a little bit more careful on what we do and with who we do it.
Well, I'm glad that we seem to be discussing some real stuff here instead of some just, sort of blah blah of like panel discussions. So that's very nice. I am still looking for more pleasant surprises. And Serge has his mic.
First of all, I want to clarify what I said about the fact that we should keep the frontiers open about collaboration. I was thinking about basic science. I was thinking about science which does not involve competition on markets. And I think that some of the research that we are doing is basic science in spite of what other people think. I think that the quantum computer is still basic science. And in this domain, I think the research about analysis what complexity in quantum system is about, whether topological qubits could overcome other kind of qubits. This is basic science, and this is not a Manhattan project which should be protected. So, and I agree with you that if you are talking about a competition on markets, a competition, economic competition, you have to be more careful. But I think that we are overdoing it. For example, when Chinese scientists are denied visas to come to Europe, if you have a project about quantum computing or quantum technology and you want to hire a postdoc from China or a student from China, now you have, at least in France, there are problems for them to get a visa, and I think this is wrong. So that's what I want to say. Now about pleasant surprises during the last 10 years, again, I will talk about the basic science. What I have noted over my career, which is more than 10 years, over 50 years, is that each 5 or 6 years, we gain 1 order of magnitude in sensitivity of measurements, in power of lasers, in precision of measurements. And I thought that a law like that, an exponential law, should at some time saturate. And I have not seen yet the saturation. And so I'm very much surprised by the fact that we are still progressing very fast. For example, take the example of sensitivity of measurements, sensing probe, developing very sensitive probes to measure gravitational fields, to measure time. The atomic clocks are still progressing by about 1 order of magnitude every 4 or 5 years. This is fantastic, and I don't know when it will stop. Another example is the control of quantum matter. 10 years ago, we were very glad if we had 1 or 2 or 3 atoms. Now we are talking about 100, and we talk about 1,000. Maybe in 5 years it will be 10,000. So even without thinking about applications, it's very surprising that we are still on a trajectory which is still exponential. And at some point it will certainly stop, because we cannot go on for that forever. But I am surprised not to have seen any saturation of this trend up to now.
Okay, so maybe things can develop better than one would expect a priori. So that's indeed a good surprise. And we are in for 3 more good surprises. Yes.
So also from the scientific point of view, so for me a big surprise has been the leverage that some quantum-inspired classical algorithms have obtained. In particular, tensor networks. So tensor networks were developed in the area of quantum many-body systems by people working on quantum information, quantum computation, and now to describe problems in quantum simulation, to try to compete with quantum computers. And since then, they have advanced so much that now they're widely used in not only quantum physics, but also in some other areas. And that for me has been a surprise. Maybe a second surprise, which is scientific, let me use a very short one, is the certified random number generation. So that's one of the applications of quantum computers. This is a quantum computer, a noisy quantum computer, that it's able to, in which people can make sure that the numbers that it's producing are random and never existed before. That's no classical analogy of something like that. and this appeared 2 or 3 years ago as a surprise to many of us.
Excellent. Oh, nice. Couple more. You can also pass if you don't have any, but it would be nice if you have some. That's for Elizabeth and Anton.
Since you mentioned my name, I don't want to disappoint you. Say something. Now, I mean, concerning the things which were mentioned, yeah, I think we should be well aware what goes on the other side and what the interest could be. Right, complete naive. It's the reason why in our collaboration with China, we decided that we accept not a single penny from them and that no equipment, nothing crosses the border. Absolutely, no. And this is going to be in the future too. This is really important. But you know, there are other things where I can see that we have some challenge. Like, for example, probably the Chinese have the most ambitious quantum communication program with satellites. I say probably because nobody of us, I think we all don't know what the significant sector of the US is doing. Right? I think that is an open issue. Now, why, and the Chinese are rather open about what their future programs will be. Why isn't there a European program which is much more ambitious? What's the reason? Why isn't there a European program? I mean, the Chinese are talking about so many satellites going up there and so on and so on. Where is the European program with a time scale and so on, which is more ambitious?
We can spend the night here and explain to you what's the program that we have. There is a program which is called EuroQCI, which started 2-3 years ago.
Yeah, and what's the time scale?
Terrestrial part, yes, 700 million euros right now.
And what's the time scale for?
Time scale is
50
now for the next 10 years.
50 satellites in space?
Yes, these satellites are coming around 2030. Already first one would fly end of 2025. And then there is even an entanglement one I learned very recently that is programmed for 2028. And then there is a whole series of satellites we should get in on board around 2030, 2031, 2032. Here you are.
Okay, let's talk again in 2033.
Okay.
Okay.
Yes, so there are surprises also in terms of we are moving. Now, since I have been told that I will be killed if we go beyond 7 p.m., now for the last one. The last one, and I'm saying this because I have the impression that the feeling that Elizabeth does not want to share any pleasant surprises with us. Okay, that's fine. The last one is, what is it that we have not discussed on this panel discussion, which I should have discussed, which is important, and which you really want to make a 1 or 2 minutes final statement that we have not already discussed. So repetitions are forbidden. Anything. If there is nothing, if we have discussed everything, then of course we can go and have a vino español, but you have some. Yes, please.
Well, like many of us, we have been working already many years in this area. And for me, that's a very special moment that we are living. And so something that we dreamt 30 years ago, now it's coming to reality. Namely, there are experiments and devices which are able to do computations that we cannot do with our best methods, including tensor networks. I mean, that's a fact. Now, the second question is, so how to proceed with that? Can we find real-world applications with that? And that's an open question. And probably we'll need more development in order to check if there are real-world applications. And second is this faraway goal of fault-tolerant quantum computers. And I think that one can cover the two goals just by exploring, doing research. This is basic research, still research, I agree with that. So what are the applications? How can we increase the times? But that's a journey that we have to take, and I think that there will be many benefits on the side as I was mentioning in my talk, probably the most important are to be discovered yet.
Thanks. Wonderful. We could already close the panel discussion with this, but maybe there are other thoughts. I will not say Anton's name, otherwise he will feel obliged to say something.
Say my name again. I just want to say that I'm really proud to be a European.
That is true. We had not said that, yes. Okay, so, I mean, it will be tough for anybody to say anything about this final sentence, but still, there might be some thing that we have not yet said.
What can we do to convince the other 20 almost member states that have still no national programs on quantum?
Yes, I see some of them nodding vigorously. Yes. We are on a good way for that. Wait in 2 weeks.
This is just a declaration.
It is indeed a declaration.
What we need is the substance.
Yes. Okay, anything else? No? No? Okay.
What about you? What do you believe?
Oh, well, actually, mine was very, I mean, my pleasant surprise was very much in line with what Ignacio said, because actually the thing which, I mean, surprises me is that we started this like 30 years ago. I was a very young postdoc under Ignacio, by the way. And I mean, who would have said we would have like companies selling those machines? And some of these companies have been founded by Nobel laureates, you know, and using the techniques that you developed and that Philippe put in optical tweezers. And now here they are, and they have done something which is quantum advantage for scientific academic problems, but not for artificial problems, for real scientific problems. I mean, who would have said it? Even when we wrote our research agenda, Anton, you know, we didn't promise this. And there we were last year, okay, at the review meeting, and, you know, they had done it. Mm-hmm. So that is really what I call a pleasant surprise. And I expect there will be more. So.
If I can add to what Anton said, he's proud of being European. I'm proud of being European and seeing that despite our age, because we're starting getting a little bit older, that we are so, so believers of quantum that we believe that we can also bring in the young generation to believe that this can be done.
I think this is really the perfect closing for this session with the 7 minutes advance. And so enjoy your vino español. No, there will be a final statement, of course. Yes. So thank all the very prestigious speakers. Thank all of you for your patience, and see you.
All right, the day is coming to an end, and I was asked to make some closing remarks. What I will not do is to try to make a summary of what has been said here. There have been said many things. We had 3 fantastic keynote speeches. It will be impossible for me to try to summarize that. I think there were 3 fantastic lessons on quantum physics altogether. We also had some comments, and also in this panel we had some interesting discussion on actually very deep and I would say complicated policy, even politics matters, like this strategic advantage, cooperation, collaboration, confrontation with partners that are outside our boundaries, outside Europe. These are indeed very deep questions. and certainly they require a deep reflection. Something that I keep also from the talk that we had by the Deputy Director General is this apparent problem that we have with European industry that is sort of shying away from committing itself to really jump into new technologies, into putting money in what we think will be the technologies of the future. That is something that is quite worrying. There are instruments like the European Innovation Council that can help, but obviously a lot more has to be done there. So I will just spend a few minutes, since I am the director of the Spanish Research Agency. I am a physicist myself. Explaining to you which is the view of quantum technologies, but more generally of high-tech research in Europe from the point of view of a national research agency. It is believed that sooner than later, a combination of a powerful classical computer connected to a few thousand qubits will be able to crack any existing code. And therefore, all our valuable information would be left unprotected. So the implications are enormous, and it is natural that as a society we take a reactive position, a defensive one. There is no question that fear is at the root of a large part of the interest that our governments, but not only our government, society in general, are showing in quantum technologies. As I said, this is a reactive move. So it is like the fear that one day there will be no chips for cars or washing machines produced in Europe, or for our laptops and supercomputers for that matter. And suddenly, the need for a semiconductor reindustrialization of Europe is on the table, only to discover that this is not a very easy task and that many cards of the deck are already given. Fortunately, Europe has a much more robust position in quantum technologies, and it is the duty of policymakers to guarantee that this remains so. We are actually quickly moving away from being reactive to being proactive. As it was 100 years ago, Europe must be the leading actor in the second part of this play called quantum revolution. Europe has the knowledge, the scientists, and with the help of policymakers and funding agencies should have the means to make the best of all the possibilities ahead. Progress in this area is very, very closely related to advances in micro and nanoelectronics, optics, computer science, and of course, fundamental physics. It's only by a wise combination of the effort and investment in all these fields that disruptive advances can and probably will be made. As someone working in fundamental physics, I'm glad to realize that history tells us once more, if there was a need, that investment in the basic aspects of science and technology always pays off. We must convince all our policymakers and our budget authorities of two facts. One I just mentioned, basic research always brings huge returns in the future. Therefore, we must combine wisely the funding for basic, oriented, and applied research. This also applies to the support that our policymakers and funding agencies must give to industrial initiative or public-private partnerships showing good promise, wisely combining the support to SMEs and startups with big projects. We want to impact in our societies in the short and medium term, but on the other hand, we should pay attention to audacious and disruptive proposals and support them at the right moment and with the proper resources, even if the promises that they want to deliver are somewhat away in the future. When possible, bottom-up is always better, more efficient than top-down. Second fact is that no one is in a better position to know the potential of a given technology or the possible scope of a new idea that the scientific community as a whole, the collective intelligence of the system. The world of quantum technologies is full of opportunities. There is an uncharted piece of new land in front of us. Expert explorers, hand by hand with some audacious pioneers, will know best how to adventure in this unknown territory. Consultancy agencies or carefully drafted plans in an office will be conservative by definition, by construction. Let us listen carefully to the scientists, then act. Tomorrow there will be presentations on quantum communications, quantum simulations, quantum sensors, quantum simulators. Let us listen to what scientists have to tell us, and then act. And now I finish. I would just conclude by thanking again the organizers, the speakers, and in fact everybody that has participated in this meeting on quantum technologies in Europe, including this most distinguished audience in attendance, and also to those that have been following us online. Tomorrow, we shall reconvene here at 9 o'clock. Thank you very much.